right, hello and welcome everyone. We're going to do a chill session here with the Flat Earth Gang over on Clubhouse. Check out the lads and ladettes over there. You can download the Clubhouse app on your respective Android or iPhone marketplace app. Wherever you get your app stores, you can get your Clubhouses, and then join hashtag Flat Earth Gang over there. Now, there was a audio issue here on my end before I got started that I wasn't aware of. So the format will be I will stream Shane's monitor when I can to get the audio for everything. And then I'll use my phone to talk. So I'll see you guys on the other side.
Well, that's because you straw man the globe.
Testing 1, 2.
What's going on?
Did somebody say something about straw man in the globe? Is that what I heard?
Yeah.
That's
Oh, oh yeah, that sounds about right.
mic check.
We'll see. Coffee said he's about to go and find something wrong with it. So after this conversation with Kat, he said he's going to find something wrong and then he'll be back. Oh yeah.
If I may chime in just for a second, what dawned on me, because I'm kind of playing catch up here, is that when they're talking about occlusion angles, the the problem that the Globies are having with this is that it's just so overwhelmingly simple. I think I said this in a chat maybe 2 nights ago or whatever on Discord. I'm like, so it's kind of a triangle you're measuring, and Alan and Shane sort of like were like, yeah, that's kind of it, and then I looked at some of the stuff on the ADL website and the measurements and observations that the community's been taking. And this is just a body bag. I don't know how you walk away from this. I don't know how you obfuscate, divert. And I'm a noob. I'm a total idiot. I'm a vaguely apprehended, inchoate understanding of what these guys are talking about most of the time, and I understood it. So I'm interested to hear what people have to say tonight.
All right, I think I got the audio situation sorted out. Thank you for restreaming that for me, Shane. Much appreciated. Do I sound better now if I lean closer to my phone? Yeah, no, does it sound any better now? No. Now it's in my head that I have bad audio. Oh, game's off. I have to go, guys. Goodbye. It's fine. It's fine. All right. So yeah, I got some exciting stuff to talk about with the celestial theodolite and my experience going over the data, making my own spreadsheet. Because as Shane was saying, we have all these different values. Nobody can agree who's the arbiter. So I started my own. And during that quest, I had several realizations. It was quite the spirit journey. I stayed up over 24 hours over the last 3 days. At one point, just trying to, when I was going over this, and one of the things I realized is like we need something to compare to that's the globe that, regardless of what was predicted or what's said about how you derive this or that, how can we, what actually occurred, right? Because we're using the position of the star when it actually occurred. So it occurred to me to just use to the refracted position of the star at the same time of occlusion from the observer location, because that's the reciprocal of what we're doing, and that's exactly how the globe would see it. So any angles that they would do would be based off of their apparent occlusion timing. So I use that as my baseline there. A lot of the analysis has been caught up on uh like how they account for globe drop, and it's like, you account for it this way versus accounting for it that way. Well, when I went over the spreadsheet, one of the things I noticed is that the way that Mike derives the drop over distance is exactly identical to the way that Jesse, like, they come up with the same amount every single time, the same angular amount. And so there's no difference in what they were doing. So the whole, like, you're double dropping globe thing, like, I don't know what any of that means. The numbers are all the same, guy. Like, there's it's all the same. And so after we got through all that, uh I started running the comparison off of the, where the star was and stuff. So the analysis has developed into three ongoing analysis. So what I have here is a spreadsheet that I'll share, and then we can kind of go over the details of page one of it. And as we walk through it, I'll get through to the relevant parts on the data, because how it said, how it's stated, like, oh, it gives flat Earth results, it gives globe Earth results, it gives concave. Well, when I went over the data and put everything in, none of that's true, and a pretty one-sided picture is painted, but it's in the occlusion timing differences with respect to the where the star was apparently and where the star's true position was with respect to the mountain peak. So we'll get into that and what the significance of that means in the measurements, because what actually happens with the numbers is there's no instance where the flat earth is conclusively off. It's just like, oh my god, I can't believe the the difference here is crazy. No. When a globe earth result, so called, is produced, it's at a location where it's indistinguishable from the flat earth results. As I was going through the analysis on the spreadsheet and changing the numbers and getting everything figured out to get the proper Steelman, and had a formula wrong there, here and there, corrected it. As I made the corrections, I watched these values change uh, multiple times over the course of the day, where it would be in favor of flat earth, in favor of the globe, by a difference of like 3 meters to like 50 meters. And you have to consider that the sky moves at, well, you could the mathematical equivalent of 30 meters a second. So there's that part of it to distinguish, and the measurements that quote unquote prove the globe um, are the difference between them in prediction. Like for globe drop is usually less than 60 meters. So we're talking, a 2-second difference where it's indistinguishable. Like it doesn't give a result that's like, oh my god, flat earth was super off. But what does happen is the when the disparity, where the refraction uh can't account for it, the time where, like, it shows by the timing differentials of the occlusion timing of the star. It shows that um, the occlusion would have already happened, like, based off of all the other instances where they tried to use it to prove the globe, where the intersection was like damn near instantaneous. So we will. I can kind of go over that now. But if anyone has any questions or anything, I've been talking for a minute. If anyone has any questions before we continue on.
No, I'm good. Let's go. I'm ready.
Yeah, I'm
All right,
with you
cool.
so far. I'm caught up to this point.
All right, cool. I'm gonna have Kat link the spread, or yeah, I'm gonna have Kat link the spreadsheet in the chat, and if somebody could, or for those who want to, they can follow along with the things I'm gonna be going over here. So here's that link. Kat, put that in the chat for me, and I'll give you guys a minute to get that link and pull it up, and then we could go over it so we could see where what the state of my analysis is and what I'm doing, and the couple of plans I have to add to it and make some little changes. But I think this is
Yeah,
a
if
really
you're
good way to represent the globe. Go ahead.
sorry, yeah, if just for the audience, if you're just listening, the spreadsheet is like essential. Like you really want to follow along with that. It'll make everything super clear. That's all.
Yeah, one of the things I tried to do was make like the relevant numbers more accessible versus like all the stuff that's used for computation. Because when you look at all the other spreadsheets, there's like, it's for me, I can't make sense of it at all. Like, just looking at it like that. So so the way I laid it out should be pretty straightforward. So if somebody from if everyone's ready, I'll go ahead and start breaking it down, I guess.
Yes, sir.
All right, so starting from column B, so A and B are linked together, but so what those values are: peak altitude. Oh, was it? I thought that was D3. Oh, okay. Yeah. So anyway, this spreadsheet is designed to be a calculator per peak and star. So if anyone wants to try to use this themselves or input their own data or whatever, all you have to do is change the green values to whatever Stellarium says and whatever your altitudes and distances were, and everything else it'll computate. So anyway, starting from B1 there, we got the peak altitude. So that's the known thing. And then we have our observer altitude, and we have our distance, all standard stuff. Below that, we have Earth radius, and then we have celestial refraction. Now, the celestial refraction was an issue for everyone because depending on what formula you use, some people agree this and that. Sometimes it deviates from stellarium, so it's hard to make an exact projection on where the star was. So, what I did to solve this is I end up using the stellarium positions for the true position and apparent position at both the mountain peak and the observer location, and I input those values, and it just subtracts the difference. So like whatever it subtracts the difference from the apparent location at the peak and the location on the peak as well. Like so basically the true from the apparent at the peak. So whatever the celestial refraction is at the time, it that's what it comes up with. Actually, hold on one second. Doesn't sound right. It is the peak observer star peak position. Hmm. That should be this value. 1 second. So instead of 10, it should be observer star apparent 10. No, wait, E18. Yeah, this needs to be it. Sorry, 1 second. I just realized nope. Anyway, I'll fix that later. No, never mind. That is right because it gives the correct value. I'm sorry, I was looking at that wrong. Anyway, so what I do is I just subtract whatever the true position was from the apparent position, and it gives whatever the celestial refraction happened to be at that time, because that's whatever it had to have been, right? Because that's where it was. So there's no argument on, oh, this formula, that formula, none of that. So we cut that out, and then we have our difference in altitude on column B7, and then we have the occlusion angle. So that's when the star was actually occluded using when the time of the star was no longer visible, and then we go to the mountain peak and we see where the true position of the star was. That's what we're referencing for our occlusion angle. And then under that we have the observer star position true. So this is at the observer location where the true position would be referenced at. And then we also have the apparent position right under that. So if you if you're on the globe and you're looking at that star, the angle would be at this position right here. And we have the true position at the peak as well, which is just the same as the occlusion angle, but I just put it in there for redundancy, I guess. And then we have the apparent position, so the refracted position for whatever that is. So that way we can reference at any time any of these relevant variables so we can know how that lines up to the actual globe. Now, under that, I have everything converted into arc or degrees, minutes, and seconds so that it's easily readable. Like I'm more familiar with the degrees, minutes, and seconds than I am the decimal degrees. So everything you input will be in decimal degrees though. And then at the bottom, you'll see the output there where it goes over the same information, but just in degrees, minutes, and seconds. So you can see what that all looks like. And then under that at the bottom, you'll see a new thing that I added called refracted lift and refracted drop. So what we can do is we can take the tangent of the distance and the celestial refraction to get a distance in meters for what that would be. So like that's the equivalent of saying like, okay, celestial refraction was, excuse me one second, I got a cough. So celestial refraction was 14 arc minutes. What does that mean in terms of like lift? Well, it lifted up 217 meters. That's what that means. So we can figure out what that value is. And we can also subtract the amount. We can take that value and we can subtract it from what their expected drop over distance is. So we can see how much refraction is actually lifting up in meters. And so when we're going through our analysis here, we can we can see when refraction is sometimes triple the amount of the expected drop over distance, and we'll get into what the implications of all that is as we move forward. But does everything make sense so far?
Yeah, I'm following.
100%.
Cool. Awesome. Okay, so the next part, when we get to the E column here, in the F column, that's where it's showing the output in the units. So it'll be in decimal degrees or meters. It tells you what the units are. But our E column here starts with the flat Earth elevation angle, and that's just the rise over run of the delta altitude and the distance. And then under that, we have the mountain altitude derived from the distance times the tangent of the occlusion angle. So that gives us a number in meters, which gives us what the angle would have had to have been to do. I'm sorry, what the elevation of the object would have had to have been to do that occluding based on that distance. And then we subtract that from the known altitude to see what the difference is, to see how close we are, to see how far off we are. And because the star was actually occluded a little higher than what's predicted from our angle, we get a negative value. But for the computational purposes, it will use the absolute value, so it'll just be treated as positive to make it easy. And then we have the distance to the peak, so we can backwards derive our distance. So when we said that it derives your distance backwards exactly, if you do it based off of one of the if you do it based off of the altitude, knowing the known distance, it becomes circular. So if you do it off of the delta altitude, the known altitude, instead of the one that you derived based off of the distance, you can you get like an actual approximation, and it's not circular because otherwise you'll get the exact value every time. So that has changed since we last spoke. I'm not sure if we talked about that when we spoke last week or not. I don't think we did. But anyway, we get the value there. So now we can compare this to how much or like how close we are to our observer's actual position there. And if there's no questions about any of that, so yeah, so for the flat Earth stuff, that's all just the plain trig. There's no refraction or anything like that. We're just like whatever the raw angle is what we're dealing with. Any questions?
No, I'm good so far.
All right, all right. So moving on, we have the Jesse modified globe Earth method, and this will soon be changed to the full Jesse method. But I didn't have his optical drop thing. That's why I ended up doing the refraction thing, so that I could just make the analysis based off of whatever actually happened. But I'll add what he thinks the globe should predict, and so we'll have that added to it. But right now, the part of the analysis that is exactly that he would exactly agree with is we have the drop over distance formula, the way that he does it by using the square of the square of I'm sorry, he uses the square of Earth's radius squared plus the distance squared minus Earth's radius. And that gives him, so for the example of Pikes Peak, it gives them 201 meters for how much drop they should be. And then you could take the arctan of that to convert it into an angle. So when you convert that to an angle, you get 13 arc minutes. And then you subtract that 13 arc minutes from the flat Earth angle, which was 231, and you get 217. So for their raw trigonometric angle, they get 217. But if you add there's a part that Jesse wants me to add, and that's to this is how they get 219 instead of the 217 that we get, and like we've been quibbling over them. Yeah, right. That's exactly what it is. So it like subtracts out some of the drop and then adds it back in this like weird way. But so anyway, when you do that, you get a slightly different number here. But when you change it to 219, it doesn't matter because the actual star was included at 222 anyway. So you know that but I will include that so that it'll have like actual geometric globe comparison for their refraction terrestrially as well, so that we can see the differences for everything, because I want to best represent by the way, if anyone has any, this is how you really calculate it, just send me the formula and I'll put it in there and it'll be added. I'll add it to all of them and it'll be incorporated, and we could look at all the different ways that you can calculate drop on the globe, because somebody just sent me a new distance formula that's really cool. It's just calculating the chord length, but I didn't even consider that as a method, and that gives a different result too. So we get different results here, but the thing that's consistent is the flat Earth one is just like there's only one way to get the flat Earth value because it's arctan rise over run. It can only be one thing with this whole globe situation of depending on what they want to account for, depending on if it's an approximation of a sphere, the exact geometric difference, yada yada. You get into all these different things, and it changes it by like minuscule amounts and whatnot. But if anyone has anything that they want me to add, I'm not, just let me know. I will put it on there. So
Wait a
with
minute.
that
So
said,
the Jesse correction, do you know where he got it from?
it's their terrestrial refraction coefficient. It's based
Okay,
off of Earth's radius. It's basically,
I
yep,
got you.
thank you. Yep. So he wants to add that in, and that's totally fine. But anyway, as of right now, no, no, right. The way I have my spreadsheet divvied up, right, the Jesse modified method and the actual Heffron method are divided up because what's often conflated in speech, and whether or not it's intentional or not, I'll let you guys be the judge, but he'll often refer to the Heffron method in terms of the actual method where you line up the true position with the peak, and use the occlusion timing from the observer location, like no problem steel manning that. But then when it gets to the analysis, they disagree on what they're deriving geometrically for what the globe predicts by this little tiny value here. And as we see in reality, whether or not the Earth is a globe or flat, from that angle, the occlusion, the star is predicted to be at 2 degrees and 22 arc minutes. So it doesn't even, you know what I mean. So moving forward with that part of it for now, I will add in the 219, but moving forward with the 222 as the position of the star for the analysis, I then derive what the elevation would have had to have been, the same way I did for the flat Earth stuff, and all that's done with rise over run as well, or just doing tangents, so and arctans. So we have our distance and we have our elevations derived from the same.
occlusion timing based off of the refracted position, and we get the distance there for that. And then I just added a distance at the bottom. If you go to column E30 way down there at the bottom, you see a value of 46,189. That'll be incorporated in like a more relevant way to read it, but that's just a test to see how the calculation went. But anyway, that's the chord length. So when they're like, you can't use 8 inches per mile, it has to be this or whatever, like it doesn't matter, we'll put whatever distance you want in, it's fine. So there's the chord length, and then so you can see that distance too now is 46,000. And then when you look at the at E13, based off of the occlusion timing, they would predict 53,000, and our observer was only 50,700 kilometers away. So in this example, if you go to column E26, you'll see a dynamic column here that displays which one was closer. So it says winner FE. So in the examples where the globe is closer and which globe model was closer, or which globe computational model thing was closer, it'll display that one first. So FE was closest by, we got 36 meters. The globe Earth was off by 125 for the elevation of the mountain. And then using the Heffron method, using the 360 for the or no, I'm sorry, using using the what is it, the 180 times the distance over 2 pi r, using that, which gives the exact same value as what Jesse gets doing his thing from column E8 there. So like, that oh, you're getting the wrong thing, like geometrically they're deriving the same thing. But anyway, using that value in the true position of the star, I continue the Heffron analysis with that, so we can see what that looks like as it plays out mathematically. So we can see the differences there. And then so at the bottom underneath column E26, we have E27, which displays the differences in in the distance that we derived. So we were off by 86 or 816 meters. The globe was off by 3,000 meters under the apparent position projection. And the way that the way that I'm deriving it for the Heffron method continuation is off by 9,000 meters. And if you do the chord length, you're off by, or you get a distance of 46,000. So they're off by about 4,000 meters, 5,000, something like that, somewhere in there. And I like the chord length one. Sorry, I like the chord length one because it's independent of the distance. We're just using the observer altitude plus the radius of Earth. So
Triangles, baby.
yep, yeah, and then also there's a column here down at the bottom that gets really significant. Oh, so real quick, let me finish out. So that's the basic backbone of everything and where all the numbers come from, and what drives the spreadsheet is all in the green columns. So you just enter those values and it'll trig itself out to infinity. But to continue on here real quick, I'll go over Heffron's method. So what Heffron is doing to derive the true position of the star, he can do the distance, or he can do 360 times the distance over 2 pi r, and it gives a value of 27 arc minutes. And from that, you could subtract, or you could divide that in half. So you could do 180, or you could just subtract or you could divide the 27. But anyway, you get 13. When you subtract that from the flat Earth prediction, you get the raw geometric globe. So whatever value you get by multiplying the distance times 360 times 2 pi, or divided by 2 pi r, and then subtracting half of that value will give you, from the flat Earth raw trig, will give you what the globe predicts. And Jesse's formula and Mike's formula both agree on that 100% every time for every measurement, always. But but like I said, they want to do the refraction they want to do the 7/6R converted into degrees per mile or whatever. So that's why they get 219. But like, yeah, like the whole discrepancy between that, and that's what held up like weeks of actual conversation, was like literally nothing. Uh, so yeah, moving forward, there's no discrepancies, and any value that wants to get added, like I said, we can just add it and it'll be incorporated. But anyway, to continue on here, um, I wanted to in this measurement, the 360 pi relation, the 360 times the distance relationship works out to be almost exactly where the true position of the star is for the observer. So I included a column to note that for all the observations, so we could compare how that geometric relationship stacks up to where the true position is, so we can analyze that later. And then under that, I have the difference there. So that's what that's for, but that's not super relevant yet for me. But anyway, and then we have the distance and elevation and differences based off of based off of those geometric predictions. And then at the bottom there, I just compare them all. And I have and like I said, these are dynamic columns. So per page, they'll change based and display the winner based off of who was closest to the actual user input that you put in on the left here at the beginning, all the green values. And then you could see here this bottom one that I added where it says refraction lift 217, expected drop 201, overcompensated by 15 meters. So that'll tell us what the celestial refraction, like how much it's lifting it up, so we can kind of compare and see what that looks like in real time. And then we have uh, the difference in position of the true position on the peak for that physical intersection, and where the star was with the apparent position from the observer location. And we have that difference displayed in arc minutes. So we can see when these occlusions happen, because our premise is, the occlusions are physical. So when the actual light source intersects with the peak, there's not going to be like this crazy extended amount of time where it's able to be lifted up, because it physically intersected with it. So it's no longer visible, even if there is a change from the star to the peak due to refraction. There's still going to be like an actual timing difference that's going to correspond to a different prediction. Like, for example, right, they get 220 2 degrees 21, or I'm sorry, 2 degrees 2 they get 2 degrees 22 arc minutes for their measurement, and that's different from our 2 degrees and 31 arc minute prediction. Like, there's an actual difference there that can be distinguished. So if the star is like physically, below that or whatever, at a 1-to-1 ratio to the refraction, then like what you're proposing is just like, oh well, the globe just, it looks like a flat earth because of refraction every time, always and forever. That's absurd. There has to be some way to quantify the intersection and make it incorporate that in the analysis. So that's what the goal of that is there. So anyway, what we were looking at on this first spreadsheet was Pike's Peak, but I'd like to go over a couple of more peaks now that we know how the spreadsheet works, and then we could go over these quote unquote ones that prove a concave Earth, ones that prove a globe, etc., and what the significance are on the occlusion differences. Dude,
Yeah, I was
And
literally going to ask you. So even when you put you capitulated and put Jesse's adjustments up in here, and it still turned out that his shit was further away. What was his response to that?
but he doesn't acknowledge it at all. He just thinks that the methodology is invalid because it quote unquote gives different results. But when we go over the numbers here, like I'll explain like what that means and like what I've noticed is that the globe will be significantly off, but when it comes to a measurement that the globe agrees with, it's under specific conditions, and the flat Earth isn't off by like a lot. It's like it's almost indistinguishable. So it doesn't prove it in the way that they think it does, and also with the occlusion timing differential, with the based off of true position at the peak and observer apparent position, his measure like the measurements that quote unquote prove the globe validate our premise that the intersection is physical, because otherwise the star wouldn't have been occluded at all, because of like it would be refracted above it. But it happened when, like, we'll go over it when we get to it. But yeah,
Yeah,
he like the globe is like a quote unquote special case versus like when things actually deviate, flat earth is the one that's closest.
gotcha.
But yeah, so yeah, that's how everything works and how it's laid out. So now we go over to the next one, right? Remember, there was a peak. This is Blodgett Peak, I believe. Yeah, Blodgett Peak. So this one was pretty conclusively flat Earth for a while. But if you look down here, if you go to column E25 or E26, you'll see that globe Earth geometry based off of apparent position winds. They were 16, they were 17 meters off. We were off by 47 meters. Is the earth a globe based on, like, dude, is it over for us? Or if we look down at the uh a or column B 39 and 49, we see that refraction is twice the amount of the expected drop. So the alignment of the true position and the apparent position intersection for the observers isn't that much. And when the intersection actually took place, like when the star wasn't visible anymore, the difference between them is 2 arc minutes. So this is an example of it being indistinguishable based off of a specific ratio. And this is where refraction has doubled the expected drop. So like it basically compensated, canceled out, and then the star was occluded based off of the physical processes. And then uh, that's 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 why it overcompensated by 1100 meters. And then so anyway, it's closer on that. And then when we get into the distance, we're off by 2200 meters, and the globe is closer by 779 meters. And then if you follow out the analysis that I was doing for the Heffron thing, it's off by 16,000. If you go by the chord length, it's at 33,000. Our observer, so they're off by about 2,000 because it's 35,000 was our observer location. So they'd be off by, actually they'd be closer to look at that. They'd be right in there. It'd be a close one on that one. And that was done that was one of Mike's. And then we have Cheyenne Mountain. This one comes out to be globe with so flat Earth is off by 63. The globe gets it by 52. And then for distances, we get 3,600 meters. They get 2,900 meters. So they're closer in that. And it's like, and so when we look at the expected drop over distance for the globe, the 142 meters, when we look at the refracted limit or refracted lift there, it comes out to be 123. So they under predict. So So yeah, they're off by 19 meters. So yeah, this is extremely close on that. But again, the true position of the star at the time of occlusion was 1 degree. The apparent position for the observer was, so with refraction, was 1 degree. So the celestial refraction between them was 9 arc minutes, lifting it up. Yeah. So like within this threshold of this area here, where the refraction is basically the same as the drop over distance, very similar results.
So essentially, um, when the peak is far enough away to where the refraction is really big, then that's when you get globe numbers or closer to globe numbers. Is that what I'm hearing?
The refraction is really big. Yeah, it's not necessarily the distance. It's also a combination of elevation, because they would get
Got you.
different refraction values for each one or whatever.
Yeah,
So
yeah,
you could, because some of them, it's like this one value is crazy, and then you look at the real tiny angle from Jesse's observation, and you would think that that would be more, but it was actually less than the other one. Or so it gets interesting with that relationship, like how it impacts it in turn, because how it impacts it for the lift is relative to the distance of the observation. So when we're comparing that, that's why it's like this little amount of refraction or this big amount of refraction didn't have that much of an impact or had a huge impact, is based on the ratio of the distance to the observation. So that'll vary in
yeah.
the so that'll vary per thing.
Okay.
But yeah, but for the most part, they're overcompensating. And then when we get to the quote unquote concave Earth ones, we'll see how we'll see what happens with the refraction differences there. Okay, so I think we were at Cheyenne Mountain last. So now we go to the next tab, and we have uh, what is this? Mount Rosa. So Mount Rosa, flat Earth, we were off by 4 meters. Globe Earth was off by 85. Our distance wise, we were off by 163 meters. The globe was off by, or the Jesse modified globe was off by 3,000 meters, and my projected globe through my analysis is what is that? So 16,000 meters. I need to add some commas in these. All right. So yeah, then we look down here at the refraction. The refraction was 48 arc minutes for this mountain. That's preposterous. And then so it gave 680 uh, meters in lift. So it overcompensated by their expected drop. Their expected drop over distance was 178 meters. So it overcompensated by 500 meters in refraction. That's crazy. Yeah. Yeah. So that's cool. Um, so yeah, when you get it, so like their prediction, like with that refraction there, to do that, it's like that's the only reason it's even close at all. We just plain tricked it out, you know? What's that? So it will be in the future. Right now, it's driven by just whatever the apparent position was at the time in stellarium. So whatever refraction they want to put in is irrelevant, I think. Well, it it'll be relevant in the analysis after, but like for right now, it's fine. Yeah. So for Jesse or for the Heffron thing, this is how I decided to do it. I did distance times the observer true position of the star. And then did I do consistent with that? Yeah, just did true position times the altitude. Yeah. Yep. So true position time. Right. Yep. 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 And then so when we go to Blue Mountain now, we have uh, flat Earth angle of 1 degree 43 arc minutes for the flat Earth prediction. We have a globe Earth drop over distance of 178 meters. Wait, this is, hang on, this, oh, I didn't enter the right data for Blue Mountain. Give me 1 second. I could do it on the fly real quick. Shane, if you want to, do you have any filler or anything you want to? I'm pulling it up now. Is my positions correct? I can just, so I just need to change the distances. Well, it's in arc minutes underneath it. No. I'm in the process of overhaul. Yeah. Week out. Again. All right. That should be good though. So just, are my star angles good? Actually, I can look it up. I have a thing. Hold on. I'll just look it up. So also in this spreadsheet, what I added here, there's a thing on the side that says notes on the right column there. Next to G, you'll see notes. There's a Canva link, and you could click that link and go to Canva and verify the positions of the stars at the time there. So if anyone's ever like, oh, you made up the number, or what I need to verify, I took screenshots of all the positions of each one and put them there, and then that's a public link, so everyone should be able to view it if they ever need it. 1 degree for true position, 1 degree true. Yep, yeah, that's solid. So wait a minute. Yeah, I changed everything except for the distance. I forgot to update it. Okay, so this is all good to go now. True position 121, 121 apparent. Yeah, we're good. Okay. So this is now, so this is Blue Mountain. This is an elevation of 3,000. A difference in elevation between the two is 926 meters. The occlusion angle was 1 degree. We predicted 104. Globe Earth predicted, what did they predict? They predicted 50 arc minutes. They predicted a little under a degree. And then the actual measurement was just under 1 degree. It was at 57 arc minutes. So it was super close to 1 degree was the actual occlusion time for the apparent. And when we derive everything based off of all that information, we get flat Earth winds. We're 57 meters off. Globe Earth is 90 meters off, and the Mike Globe is off by 440 meters distance wise. We're off by 3,000. Globe Earth is off by 5,000, and The other globe Earth is off by, is that 45? Yeah, 45,000. So, all right. And then let's take a look at the refraction here. So the refraction impacted this measurement by lifting 470 meters. And so that undercorrected by 47 because the expected drop was 294 meters, or I'm sorry, 194 meters. And the occlusion timing difference between them here was 2 arc minutes regarding the true position and the apparent position. So 2 arc minute difference there on when they were separated, or how much they were separated by. And that's a 10 arc minute refraction correction there. And their expected drop as an angle was 13 arc minutes. So that kind of puts it into perspective. And we have Green Mountain next. I'm gonna make sure I got the right figure for that. And I don't actually. So 385. And distance is 52,960. Okay. And let me make sure I got my star positions correct at least. Green Mountain. There we go. Update this link. One second, almost done here. Just making sure I got the right angles in here. 104. Yep, we're solid. Okay, angles are correct. Just had the wrong altitude and distance. Okay, so flat Earth, we are 10 meters off. Globe Earth is off by 80 meters. Flat Earth wins in the distance as well. We are 570 meters off. Globe Earth is 4,561 meters off. And using the Mu globe, it's off by 42,000 meters. And here we have refraction lifting 323 meters. Their expected drop was 220 meters. So they're overcompensating by 103 meters of refraction there for that. So it's like to even compete or be close, I mean, it's literally made up in the refraction. And so and here we have another example of the true and apparent position being close to the peak for the intersection. The difference between them in position is 4 arc minutes. So, and then next we go to North Peak. So that's the next one down there, denoted by NP. Now this is where it gets crazy because we're told one of these stars specifically gives concave results, but it only gives messed up results if you confine it to the analysis of the altitude of Greenhorn. But if you do it at the altitude of North Peak, and they're like right next to each other, so in the video, what you'll see is the star comes down and it gets occluded at the edge of the frame on the video, and Jesse has done a pretty good job of like deriving where that position is on the mountain there. Like I would never try and dispute it. I'm pretty sure he's nailed it spot on. So I have no idea why optically it looks like it's in the corner of that spot, but when you trig everything out, it gives the results that correspond to that mountain peak. So again, I think it kind of proves. I think the celestial theody kind of proves itself there because we're not concerned with like where things look optically is just like what time was the star visible, when was it not visible. Okay, if we make a triangle based off of that, we end up with something that corresponds to this mountain peak intersecting it. So that's like I said, they're right next to each other, and it was often it's at the very edge of the frame, and uh, that's all I can offer on that.
Triangles, baby.
Yeah, but anyway, when we triangle out here, we are victorious in the elevation. We're off by 500 meters. Globe Earth is off by 1,000, and Mu Globe is off by 1,200. And then when we get into backwards deriving our distance, that's just deriving. I have backwards stuck in my head. When you solve for the distance, you get 30,000. We're 30,000 meters off. The Gamma Globe is off by 192,000 meters, and Mu Globe is off by 339,000 meters. And this is where it gets really interesting because the refraction impact on this is massive, right? There's only a 21 arc minute, or there's a 21 arc minute refraction correction here, but the impact it has based off of this distance here, because our distance to this peak is 130,000 meters. So the impact of lift that 20 arc seconds, 21 arc second, I'm sorry, 21 arc minute lift correction has, it gives 821 meters of lift to the globe, and it was still off by 518 meters because where the star's true position, and this is where it gets really crazy because the true position of the star at this time is predicted to be below Earth curvature even. It's 11 arc minutes below the ball. So like forget about the mountain peak. It's like that's done in whatever angular size the mountain peak is, that thing's below. Like, and we're talking the true position, like the thing that did the intersection that quote unquote proves the globe and gives globe results and stuff. We're talking that is below the Earth curve by is below the horizontal, they say, by 11 arc minutes, and it's still visible. And so the difference there from true position to apparent position comes out to be a 40 arc minute difference. So like in other words, this correction just makes it a globe just because it has to be. There's no reason like this their correction timing difference versus true and apparent here when consistent with all the other measurements is absurd for them. Like it's like the ultimate special case where it's like in this scenario, the refraction like it got occluded. It happened almost exactly, at the same time. Or I mean, they're not that far apart. Rather, that should be how it's said. They're not that far apart. But in this scenario, there's a 40 arc minute angular difference there. That's that's the ultimate special case that I've seen. So. And then that goes on for 3 other measurements. So there was 2 other stars that confirmed hit that peak. So we know what the values look like when it's a star hitting that peak. So when the star in question regarding, giving concave results when applied to the wrong peak, if you apply it to North Peak, it doesn't give concave results. It gives results that correspond to 2 other stars that were measured at that peak. So I don't know, like what to do with that in terms of the contention, but that's just what the trig shows us there on that and where the true positions of everything was. And so the globe was off, astronomically every time. But again, we're off in distance by 30,000. So, but Gamma Globe was off by 180,000. So, and with the new formula, I forgot with the chord length, they get 30 or 73,000. So yeah, they're off by like 50 something thousand, 60 something thousand. Yeah. Yep. Yeah, that's super important. Thank you. Because yeah, when we were saying you can backwards derive your distance exactly, you can, but only if you do it based off of the distance and the occlusion angle, and then you'll always get it back to the distance if you derive it off of the elevation based off of that because it already incorporated the distance in there. So you can technically do that, and the globe was off on that because the angle is smaller. So it it's like kind of unfair, but also so anyway, I included it so that it's derived independently of it, so we can see like in reality, like let's say in reality we were trying to find our location, with these occlusion angles and stuff, like how close would we be? This is what this spreadsheet is showing us. And we're seeing the results from the plane trig are more closely matching the locations where refraction doesn't double or triple or exactly equal the amount of drop over distance. And I think that's one of the most significant things that Mike was putting forward because, I mean, he's got the whole spreadsheet, he's got a graph on it, and it shows the refraction positions on it. It's like they overshoot it, and we're looking at that, right now, just looking at the raw stuff from what actually was measured in reality. All right. So to continue on here, we'll skip the next three because those are all North Peaks, and we'll go straight to Getaway Mountain. That was a mountain that Kat and I did, otherwise known as Catalan on the streets. All right, so here we have an elevation altitude for the mountain of 750 relative to our location distance of 48,000 meters away, real close to 49,000. And then we have our predicted angle to be 53 arc minutes. And for the globular prediction, they are at 39 arc minutes.
You on GM, right?
What's that? Yes.
The peak you're on is GM.
Yep.
All right, cool. Well, what'd you say
Yep.
the peak angle was? I'm sorry. I mean, peak
Yep.
altitude.
The peak altitude, the delta altitude from B7 is 752.
All right, I'm with you. Go ahead.
Yep. So the angle comes out to 53 arc minutes, and then for the globe they predict 39 arc minutes, and then when we do celestial, or when we go with what was actually measured, the occlusion angle for them was 45 arc minutes. So we'll reference that for the rest of what the globe derives. So for their elevation, they were off by 110. We got 104. So like not much difference between us. We were both pretty close. And then for Moo Globe, we get 480 off. And then under that for distance, we're off by 7,800 meters. Gamma Globe is off by 8,400, and Moo Globe is off by 86,000. Is that right? Yeah, 86,000. Wait, yeah, 86,000. And then the chord length is off by, they get 44,000 meters. They're off by 4,000 meters. Chord length might actually be closer on this one because we got 57, so we're off by 7,000. Chord length might be closer on this one actually. But which one? So it's the difference in elevation over the tangent of the occlusion angle. And it came out to that. It seems a bit off because using B10, using the same thing with the delta alt for, oh, wait a minute. Yeah, this hasn't even been updated. gamma delta, GM delta, GM delta. Okay, so it's using the right elevation, and it's using the true position from the observer distance to P. So observer true position, yeah. So I'm using their true position of the star for the analysis, like as if it was, you know how we do the true position for us for flat Earth. I'm also doing a true position globe for the observer. It means they have a different. They're using it. It's a completely different angle. That's why it's off so much. Yes. Well, times the altitude. The distance isn't. I'm deriving the distance independently, so it's just based off of the altitude and whatever the true position angle is at the time. So like I continued out Mike's 360 times distance or 180 times distance. I continued out that analysis using the true position of the star from the globe perspective, because we have one for basically the apparent position based off of stellarium is what I'm using for the globe. So this is just all. Well, yeah, no, but this like the Mu globe analysis, that says like Heffron method or whatever. That's just well, no. Globular Earth Mu is the Heffron continuation of that mathematical relationship with no additional corrections or whatever, and just using the true position of the star. So he might not even he doesn't even do that. I just did that because I have everything else covered and I have all this math here, and I figured why not throw it in there. So like, and also because like how it predicts the true position of the star. So to continue that out, I wanted to see the difference in the true position of the star versus where it would predict with distance times 360. So that's where all that is coming into. But like that's not super relevant to the analysis. Like when we talk about globe being on or off, it's mostly in relation to gamma globe because that's the one that uh, is deriving it from the position of the thing, and then uh, agrees with the drop over distance and all that. Yep. So let's see here. Okay, so that was Getaway Mountain, and we look at the refraction here, 22 arc minutes, and we scroll down to how much that lifted up in meters, 326 meter lift. So it overcompensated from their 188 meter drop by 138 meters. That's pretty crazy. But then again, they're like I said, they might get this one back on the distance because I think the chord length is only off by about like 5,000 or 4,000, something like that. So anyway, that'll get incorporated in there. But it's like how many different approximations do we have to use to get a good globe? You know what I mean? Because this one doesn't like yeah. That's what I no that but that's the point of this because like nobody could agree on what to do, and it's like we'll take all globes, whatever you want to do to get the distance, whatever you want in here, I will put it in here. Yeah, yeah, we only have one consistent method, and that's arctan. That's rise over run and other tangents. That's all we're doing. So the fact that they need 17 separate analyses. But I'm happy to accommodate, and I've learned a lot from this, and it's been a lot of fun. So, um, let's see the intersection here, though. The relationship between the true position and apparent position with respect to the peak and the observer location is only 26 arc seconds. So that's we get this difference here where it's like, okay, so the occlusion happened, physically when it intersected with that peak. But then we look back at the North Peak scenario and it's like 40-second difference. That's, what are you doing there? All right. Moving on now from Getaway to Hound's Tooth. That was another one done by Catalan, where we just pulled into a parking lot, aimed the Sea Star at this back mountain, and hit up an emergence, I think it was. Or was that one an occlusion? I can't remember. But anyway, what we got on this
Rising.
one was that
It was
occlusion?
emergence. It was
Emergence?
emergence. That was
Okay,
rising. We were looking.
gotcha. So the difference in our position was for globe drop predicts 6 meters of drop, and when you math out the occlusion, then like if you look at the left here, the true position at the occlusion time versus the refracted position and all that, like they're basically identical here again. And you'll see at the bottom E28 column here, there's only a 19 arc second difference from their positions there from when we no longer see them. And so that fully substantiates the method and occlusions and all of that. So when you have these like discrepancies where it's like, 40 10 plus arc minutes is I think is like is insane at this point, because it clearly doesn't physically happen at that time. But anyway, when you trig everything out, we go down here to E26. We see flat Earth is off by 5 meters. Gamma globe is on by 4.7 meters. And Mu globe is off by 18 meters. And then we have Gamma globe closer in distance. We're off by 29 meters. Gamma globe is off by 25 meters. So there's like a 5-meter difference between us. It's preposterous. It's like, is that a big, like, do we confirm globe, guys? Is it over on this one? And then Moon globe is 97 meters, and then the chord length on this one, what's that? Yeah, got it by a full meter. Let me make sure this is right. Houndstooth, alt radius, occlusion time. Looks good. Okay, yeah, so their chord length on this one is way off. It's 8,000 meters. So I don't know what happened there, but that did not work out for them at all. But it may be because the distance is so small that it. Oh, that's what it was. Okay, yeah. So yeah. Okay. So
It's
yeah,
also a very large angle. It's 10 degrees, right? This is the anomaly in this entire sheet.
10 degrees. Yes, it is. Yeah, it is a big one. It is the biggest angle and the shortest distance ever done. Yep. And then continuing out. Oh yeah, sorry. So so again, the occlusion timing difference in position was 19 arc seconds when it was no longer visible. So the relationship between physical intersection and occlusion timing is definitely substantiated here. But then we get to Jesse's Blend Mountain measurements, where the first one here shows a difference in let's go over the predictions real quick. So we have a difference in altitude of 607 meters, and we have 20,000 meters in distance. And so for our angle for flat Earth, we get 1 degree 34 arc minutes. For the globe, we get 1 degree 28 arc minutes. Or no, I'm sorry, 1 degree 30 arc minutes. No, that's what refraction. Sorry, we get 128 raw glob, and then the occlusion timing was 1 degree 31 arc minutes, and then deriving everything off of that, we go down to column E26 again, and we see gamma globe wins. Flat Earth is off by 81. Gamma globe was on by 26. And Mu Globe is off by 158 meters. And then for distance, Gamma Globe is closest. They got 1,000 meters, and we were 3,440 meters. And Mu Globe is out there at 7,000, and the chord length comes out to be 23,000. They're only 1,000 off. They might be closer than Gamma Globe, but have to add that in later. But the chord length seems pretty close on that. So again here, indistinguishable, right? There's an expected 38 meter drop. The refraction effect over this distance for 19 arc minutes of refraction gives them a lift of 125 meters. So they're overcompensating by 86 meters. Like this whole measurement here, intersection timing wise, shows that there's an 8 arc second difference. So it shows that it's just the flat Earth's not like horrendously off. It's at this point it's indistinguishable. And like I was saying, as I went over this analysis and was changing some of the stuff and getting the formula corrected, I watched this thing change from flat Earth wind to globe Earth to flat Earth, multiple times. This measurement distinction here isn't significant, and then the refracted limit is like, what is that, 4 times the expected drop as a refraction correction. Like that doesn't prove the globe. So he's doing the refraction thing, right? That's why he gets 219. So when I update this, instead of being 1 degree 28 arc minutes, it'll be whatever their refraction thing is over 22,000 meters. So it'll change it by a couple, but that doesn't even matter because the measurement is although it will be interesting to see if they over predict on this, because the occlusion timing, that's what the occlusion timing is. We can't change that. So that's where it was refracted at the time of occlusion. So anyway, when we go on to the next mountain peak here, we have a 4 arc minute difference in the intersections, and same situation with the true position, apparent position. They're very close to each other. We have an expected 130 meters of drop. The refraction correction is basically double that. It gives them, it's a 23 arc minute correction, and it gives them 281 meters of lift. So it overcompensates for them by 150 meters. Like none of this is screaming Earth's a globe to me yet. But anyway, when we get down to the distance and elevation analysis, we got 172 meters. They got 121, so they were closer. For distance, we got 15,000 meters. They got 9,700 meters, so they were closer. And then for the chord length is drastically off. They're at 44,000, so that's no good there. Or no, wait, no, sorry, that's the full amount. So 44,000 minus 4, so they're 4,000 off. So chord length's actually closest here. Chord length would be closest here. All right, and then we got one more Blend Mountain here, but again, same exact scenario, but this time the refraction difference is 18 arc minutes, and it gave them a lift of 68 meters, and their expected drop was again 38 for this location. So when we derive the elevations and everything, they were closer by 62. We had 182 or 181. Distance wise, we had 8,900. They had 2,400. And then for the chord length, 27, they're about 5,000 off. So they're They're pretty off on the chord length there on that one. And then we got one more mountain over on the side there. That's VS2S. That's my buddy Goose's mountain. Shout out to Goose. We have an observer elevation of 4 meters above sea level. We have a peak altitude of 1,400 meters. And we have a difference in altitude of 1,420th meters. And then we go over to our trig predictions here. We get 4 degrees, 51 arc minutes for flat Earth. Globe Earth predicts 4 degrees, 46 arc minutes. And what was actually measured was, for them, was 4 degrees and 57 arc minutes. So when we go through everything, they derive an elevation of 1,044 meters, a distance of 16,000 meters. And when we get down to the analysis here, we have flat Earth winds. We're off by 19 meters. The globe Earth got 28 meters. So we were closer by, some insignificant who cares amount. And same with the bottom here with the distance. We're closer with 230 meters. They're off at 330. So then their chord length comes out to be 4,000. Ooh, that's gross. Their chord length super off. Oh, this is referencing the wrong one though. So can't no chord length for this one yet. But yeah, so we see, and then so for their expected lift over the distance there, they got 49 meters in lift. Their expected drop was 22 meters, so they got double the refraction again, which creates this just like this indistinguishable measurement between the two predictions based off of the refracted position and the true position being intersected by the mountain peak, but completely substantiating the fact that occlusion happens with respect to the true position and the mountain peak. That's what I've really learned from this, is that is substantiated AF. And when you get to, like, the globe is either like way off, or flat Earth is like indistinguishable from globe under these, like when the specific thing happens where, with the refraction being double the drop, or like just the amount and the distance, where the true position and the refracted position are closely in alignment. What's that? Oh yeah, dude. What up, Dr. Mike? Dr. Mike, I owe you an apology, sir.
Love means never having to say you're sorry.
Dude, when you first introduced the J Factory, like a week had went by, we were trying to figure out how to like derive it physically, or how to reproduce it and stuff. And you were like, yeah, you just go there, you just go into Stellarium, wait till the true position is at what the globe predicts it is, and you're good to go, and it rounds it all out. And it was like at the time I was like, it didn't, like, it made sense, but I was just like questioning it, like it didn't seem right. And then I realized when I was making my spreadsheet, you need a globe to compare it to. And when we were going through all of this, nobody could agree on a globe. So you were like, okay, here's a perfect globe. Here's what the perfect globe predicts. We're comparing against that. So it's like, it's not that, you did anything wrong. Like, because people were saying, like, he introduced this method, it's a fraud, he's a fraud, all this stuff. And it's like, bro, dude, you were trying the hardest to like make the perfect globe to make everyone happy. And like, I felt really sympathetic to that, because I experienced that the other night, where at the end of the night, I finally had enough globe steelman where I was like, I think I've satisfied every possible globe position, because it's crazy to, what we had to go through, because these measurements are so straightforward when you look at the data and what it's showing with the refraction and all that. And then to go through and have to like backwards figure out what the hell even is the globe that these people think they believe in. It's been a very enlightening process. And shout out to you for going through it all.
Well, I'll take the blame for not adequately explaining what the J factor was doing and how it was working and why it was valid. And I'm glad that
About
some
your
people
time?
are finally beginning to pick it up.
Oh man, I still gotta wait to lock the door. Lock the doors.
Oh, someone's hot micing.
Hold on, let me
Yeah,
see.
that was me, guys. Sorry.
All right, go ahead. Wait a minute. So, Alan, you were you needed something in your calculations, and you were like, "Well, shit, this J factor thing, this will work right here." Is that how you came to the conclusion?
Well, it's not that. Yeah, it was like you need something to compare it to because the whole time that it was being projected that Mike was like doing something fraudulent, Jesse had done his own independent analysis, which I don't disagree with, by the way. But he was custom adjusting the elevations of the mountain peak based off of the occlusion timing. But he, did it through a ratio of his camera length and using a ruler and all that stuff. Like, so I don't disagree with it. But he introduced his own J factor, so to speak, because when you adjust these measurements with the raw trig, it goes in between flat Earth and globe Earth. So it doesn't. It's literally so indistinguishable at that point. The difference between the two is nothing with their lenient with their unlimited lenience and refraction. But but yeah, and well, even with that, like I said, it's not even they're only quote unquote they're only they only like get globe measurements when it's indistinguishable. You know what I mean? So it doesn't when there's no difference between the two. So and then we have examples where they're just completely off, which is and we're just doing plain trig here. So, but I think the relationship with the true positions and the how much refraction lifts per measurement is super interesting. And their expected drop is, often the exact amount or double or triple the the lift that they're getting out of their refraction correction.
Hey man, so Cat ran coffee off. I think he was the only one that really had an issue with the calculations. Um, and who else? I think Cat did battle earlier today too. So all our globals, we got one on stage. I don't know if he's got anything to say. Uh, Ray Diaz, are you satisfied with the presentation? Let's see. I guess
Hey
so.
guys, it's me. I'm Ray. I'm a flat earther now because of
Hey
that present.
yo.
Oh no way, Ray!
Yeah,
What's
no.
up?
Hey man, I'm not that optimistic. What's up, Thad, man? You just gonna say something, bro?
No, I was giggling with Alan there.
Yeah, I'm not sure we ain't that lucky. We ain't that lucky. So I know we got a couple in the goo. My brother Hakeem, you good down there? You got any questions, Elsa? So Elsa's he's questioning right now, right? He's FEQ.
Oh yeah,
Yes. Yeah,
I,
I
yeah.
I
remember
see
those days. That's what's up.
I
Yeah.
see Redundant bounced out of here.
You said what?
Redundant bounced.
Yeah. It was a bit much for redundant. Yeah, it was a bit much for. Like I said, most of the and my man Teddy's down there, but Teddy don't be having no questions for real. So I think
Well,
we.
sorry, not sorry that I cooked up coffee yesterday, gentlemen, but that was nice to get that sorted out for sure. I'm
Nah,
sorry he had problems with his triangles and angles, though.
Nah, Mr. Wiggles needed that.
Yeah,
No
it
worries.
was
He
Yo, who
said he's
coming up with
coming
these
back.
names, yo? Redundant and Mr. Wiggles. Yo, that's crazy.
Yeah. Nah, he said he's coming back. He said he's gonna find a problem with it, and he's gonna come back, and hit you all over the head with it. So just
You know,
just when you think you've won, he's gonna come out of nowhere. Watch,
dude, he's like the bad guy on Inspector Gadget.
Dr. Claw.
Yeah, he's just lurking in the shadows. Like you don't really
Yeah,
know
he's
what he's
there.
doing, but he's always behind it.
Yeah. He's there.
Hakeem down there. No questions, Hawk.
Before moving forward, can we just give a little round of applause for that excellent presentation?
Absolutely.
Oh yeah, no, that was dope, bro. That was real dope. So I'm actually liking the way that the like the observations are kind of, the more you get, the more you flesh it out. Seems like we're getting more and more information, which I think solidifies the position. So no, this is pretty dope, man. I'm impressed.
Guys, can you lay out exactly the tools we need to make an observation like this? Because I'd love to do one
Yep.
as well.
Yep, you need a recording device, like for simplicity and like ease of use. If your device is able to be synced to GPS time, that would be super dope. So when you create your file, everything's all time stamped, and so you know when you started your recording, you know what time it was, so you know when the star was included. That'll be super useful. So you just need a recording device that can do that and distinguish a peak at night, and then as long as you can see stars and distinguish a peak, you're good to go. And then you just need to record your latitude and longitude of your observation location and whatever peak you're observing. So you can use Peak Finder app to look up what the peak is or whatever you need to do for that. But you just need that peak information so we could run the numbers off of that, and everything else can be backwards figured out after you get your observation. So you don't need to worry about figuring out any predictions where stars are going to be. You don't need to figure out your distance or anything. Just show up, record your location, record the peak you're looking at. There's an app, if you're using Android or iPhone, there's an app called Peak Finder. It's $5 if you want to spend the money. It's for like ease of use, but they have a website you can use. Just plug in your coordinates, look it up. It'll pull up that camera on your phone. You just look around you. It'll overlay the different peaks relative to your location, and you can figure out which ones you're at, and that'll be super useful. So that's all you need, man. Just recording device, know what time it is, and know where you are, and what peak you're looking at.
For the
The type of
method,
recording device is like a C Star or a P1000, right? Or P900, something along those lines,
Yep,
right?
or
You're
a
going to need
telescope
something
that
of that
records, like
caliber.
whatever people have that can see at night and distinguish a peak.
for that part of the method, I recommend tripod mounting whatever you're going to be shooting with, and set that up in the day, maybe an hour before sunset, and get
Yeah.
a day shot of the peak, and then don't move the camera, and shoot that same angle later that night, and
Yes.
you'll get perfect superimposition.
Yep. What Stone said is super imperative. But if conditions arise where you have to change position, or the cloud comes by, you need to move or whatever, um, you can fully set up at a different location and figure out where you were at previous. But having that daytime reference for the silhouette, so that when you go and do the superposition later, is critical. So if that becomes an issue, that's how you could fix it or figure out the actual location. Is you would have to go back and get a daytime picture for comparison. And you don't even have to use the same device to get the picture. You could just use your phone camera or whatever, as long as you have the peak there, and then you could bring it into your relevant video or editing software and figure out where the camera was at. So yeah, there's just been a lot of like empty rhetoric surrounded the celestial theodolite. Like a big thing that we're encountering now that we've got all this hashed out and the discrepancy over 217 and 219 and whatever has been sorted. What the arguments we're getting now is like, this method is rubbish. This method's rubbish, mate. I don't agree with your method, mate. And yeah, right. And then, negative coordinates or whatever. And it's like, speaking of negative coordinates, one of these stars at North Peak was below the ball. Like if the ball doesn't block a star coming in, then nothing would. Then the star's a freaking laser, dude. It's just shining right through the ball. Yeah, yeah. If refraction is the same amount, double or triple what you predict, then it says nothing about ball. Like it says nothing about the uniqueness of the where we live or to prove or disprove anything. That's insane. Like, oh, my drop over distance is 30 what was it, 38 meters. My refraction correction is double that. What? That's not like, get out of town, dude, as they say. So yeah, I think the facade of like the rhetoric is, now gonna, I mean, they're still gonna do it, but we have an exact spreadsheet to like show all possible sides of it. And the big factor for me was like looking at this difference in star position true versus apparent position for the observer at the intersection time, at the occlusion time. And it's like you could see what they did.
Yeah, it's called an anchor bias, where the first thing you hear, like you assume, like is automatically your default position, and so that's why the pre-smear is such an effective tactic. So the I think the next challenge now is, because what you guys have done is really dope, right? So the next challenge I think we have is to be able to communicate this in the grand scheme of like the flat earth understanding, right? Because to be able to sit kind of through your presentation and follow along with the charts, like that doesn't translate well into kind of conversations, right? And so I think now is just figuring out the best way to translate this information into everyday language that we can fit into conversations when we're having, like when we're talking to people about the mechanics of the world. You see what I'm saying?
Yeah, absolutely. So I think some good rhetoric or whatever that you could use would be that, based off of these occlusion timing, is what we learned is that celestial refraction often is double or triple or equal to the amount of Earth curvature. And the only reason that the measurements even get ambiguous at distances is because of this extreme lift that that they're allowed to compensate for. Just using the raw trig, we're way closer when that ratio isn't at play, and that's and even when we're off, like we're not off by much. So it's like it's indistinguishable. It's like we're not even off. Like it's hard to say off when you're off by 5 meters.
Mm-hmm. No, I get you. All right, that's a start, right? That's not really a soundbite. Like a lot of times we having conversations with people. So unless you're in the weeds with somebody, right? Then yeah, you can we can walk that through, right? And then people will say, well, what are you talking about? Then you bring up kind of where the information comes from. All right. So I'm thinking more about, all right, let's say we're not in the weeds, we're having conversations and people are bringing up instances of how refraction is doing what and what's Earth curve and what's not Earth curve. That's more what I'm thinking about, but that's not something we got to come up with right now. That's kind of where my mind goes. Like, all right, how do we translate all of this data, all of this information into something digestible that we can help people understand or use to help people understand like why it's important. That's all. It's good stuff though. Yeah. Yeah. Right. Exactly. Exactly. No, that's not bad. That's a great start, Shane. I fucks with it.
Yep. Yo, Shane, will you do me a favor and unmute on Discord so that people can hear you talk?
Yeah.
Because I have your audio relayed through. Yeah, you know what's up.
I forget.
Thank you, sir. There we go. May or may not have anyway.
Blocked me out the whole stream. That's cool. I figured that out immediately as soon as you said it.
Somebody was like, "Who are you talking to?" I was like,
Fuck.
Oh wait, they didn't hear Shane what he just said?
Anything the whole time, but I think we're good now.
Yeah,
All
we're
right,
good.
all right. Well, shit, you're gonna have to repeat what you said because that shit was important, right? Did they hear me at all, Alan?
Yeah, no, they
Yeah.
heard you guys. Yeah,
Everyone but me.
All right, so they heard me. So yeah, you might want to repeat what you said because what you said was actually really good. So when we're talking
yeah. Go
about,
ahead. Go ahead, Shane. Give us another whirl, dog.
yeah. Go ahead. All right. So remember the question was, how do we fit this into a just a practical everyday argument, not when we were into the weeds. So go ahead and repeat that so the people can hear it.
Right. So I was mentioning that the way I would work it in is when you're doing one of the tenets of our discussion, when you're arguing over, geometric Earth curve versus optical Earth curve, boats over the horizon, is the bottom up obstruction being created by, optics and the observer height or physical geometric Earth curve. And I think you can wheedle in this conversation with like, well, in addition to the argument for it being optics based, meaning you can present a scenario where the inverse would happen, where a top-down obstruction would happen at a tall building. If you approach it and walk slowly closer to it, then the information loss occurs top-down instead of bottom-up, which is the inverse, which meaning you've replicated the circumstances to create an optical effect in the other direction, solidifying the fact that it is optics. And then you can also say like, hey, another way to differentiate would be the celestial theodolite measurements, which does a great job of differentiating optical versus Earth curve. And unfortunately, regardless of the 3 different ways we're accounting for geometric Earth curve, none of them are actually sufficient to accommodate the occlusion timing of these myriad of examples. I think that's the way I'd work it in, just to differentiate, one of the tenets of the argument, physical Earth curve versus optics.
Hey man,
So pumped I remembered that. Sorry.
All right, Shane. One more from the top.
Yo, yeah, say that 3 times really fast. Nah, that's all right. Good shit.
It's tough to work
But
it in.
yeah,
But on the other
so
hand,
we argue for mutual exclusivity, right? And we have this data here. We go over it and we see that the globe is off. Like, and when the globe is off, it's like, atrocious. And then we get to scenarios where it's indistinguishable between the two. So I think it's pretty evident, which model is closer
on
to
on
use if you're
on the other hand, dude,
like.
besides people like they wouldn't know this argument, and the globe is based on rhetoric. So if you talk to any other glober who we haven't already attacked with this, they're going to be completely, surprised and taken off guard, and you're going to be able to beat them up all day with any of the measurements because their whole thing is based on the rhetoric. They have to refer to the book and see what the answer to your question is. They're not allowed to critically think on the spot to come up with what is effectively a new argument, and they can't retort to that. Sorry, dude.
Yeah.
Yeah, that's the other thing, right? So it's so new. Yeah, I think even a lot of flat earthers are still just kind of like we're getting our minds wrapped around it and kind of the implications and how to work it into in the conversations, right? So we talk about it, but figuring out a way to work it into a conversation. Hey, we got to workshop that shit. And then the other thing is, because even the Globers haven't heard of it, they're going to automatically start calling Cap. Like it's you're talking above their heads is kind of how they're going to feel. So now the question is, how do we get this information out there to kind of the flatosphere, right? Where it can be referenced and people can look it up and all of that kind of stuff, right? Because right now, I guess in the hands of a small niche group of people. So how do we get it out there? What do you guys think about that?
I'd refer them to Alan's work and Mike's work with the links. Kat provided all the links to Mike's work earlier, and in this presentation, I think Alan said he had a link there to a few different things. Alan, did you share the link to the published
Yeah,
documents? Or
yeah, Kat shared a link to the spreadsheet, and then on the spreadsheet, there's a notes section that has a link to all the stars positions on Stellarium in Canva.
So you know what I'm thinking? Y'all know the video that Stone shared about the shadows,
Yeah.
right? I'm thinking there needs to be something like that, right?
Mm.
With some visuals that go to it.
I
So
said this
people
the
Uh-huh.
other
can
day.
I
yeah, with
feel
some visuals
we,
that
it.
go
we need to
to it.
hire that one brown, one blue guy, man. He's awesome.
Right. I don't know. We going that's what I'm thinking. I'm like, yo, this would be dope.
Yeah, I did make some visuals, but they don't really transfer well in Clubhouse. But yeah, I think we should have an animator do it so you can see like the geometric Earth curve represented, refracted Earth curve being like what does that represent visually? I think that would be super helpful.
Yeah. Yeah, I think that would be dope. So yeah, something like that. I think that would be amazing. Right. Something that gets like it gets people a visual as well as an understanding of it. Like it'll drive it home. Right. So something that can go viral, something we can just use to post up, something the average person like that's in the flat earth can put up on their TikTok, right? So I think that's kind of the best way to get the information out there. Something nice, digestible, minute 30-second long ass fucking animation or some shit, right? So that's what I was thinking when we was up here talking. I promise you, that's what I was like, yo, this is dope. How do we get it out? We need something that people like. Everybody loves fucking cartoons, bro. So I'm fucking mid-40s, like I still love cartoons. You know what I'm saying?
Did you
I
guys see
love-
the latest episode of Dragon Ball Z or whatever?
Yo, hey man, don't threaten me with a good time. Um, yo, so yeah, no, I like it. So that's what I'm thinking, man. So any animators out there, yo, get a hold to it. Anybody that likes working with animations, I think y'all should get a hold to it and just put together something quick and crude. That'd be dope. This is just my suggestion.
Man, that'd be dope for Stone's thing too, man. His shadow says.
No, 100%. Right. So I think we got to break this. So if we break the concepts down to the lowest common denominator, I think it severely helps what we're doing, which is just spreading information.
Yeah.
You know what I mean?
Yeah, no, it's definitely something to consider and figure out. That's the plan now. So
Yeah.
that's why I've kind of been doing the updates and every week, just trying to see where people are at on it and how I can help bridge the gap on it.
No, that's dope. So I think to keep having people do the observations and participate in it, so that we get more and more data, more and more observations. That's one end of it, right? But at some point, it's like, all right, we got enough data. We got to start spreading the word. We got to get this thing out here
Yep. Yeah,
because
we
it's
got
super
enough data.
important, right? So
Yeah.
it's like, yo, it's not enough that you have a great product, right? More importantly, is how you market that product. And so, um, like the best thing you can do when you got something super dope is to let people know about it. And so I think that's kind of where we need to focus on now, or at least put some IQ points towards, um, and some effort towards marketing this information because it's that important. Know what I mean?
That's a good point.
Absolutely.
Yeah. So now that's what I was over here kind of thinking as we was talking and stuff. Like, yo, this is some monumental stuff. Especially because of, like, the way it came about. It was super organic. It came about the way that everybody comes to flat Earth, which is
Yep.
accidentally as a way to
Yep.
prove that the Earth ain't flat. Right? It's like, hold
Dude,
on. Let me go ahead and
we
prove
all,
this shit.
I think that's the actual difference. We all tried to prove the Earth was a globe without assuming it first. And
Fact.
when we did that, it was GG. We were like, oh shit. Can't beat that, boys.
Exactly. Exactly. And so you sitting here with nothing but your pride in your hand, like, oh shit, what do I do now? And so I think the dopeness of this is that it came from somebody who was sitting where everybody was, trying to prove that what we knew was right. And he came up with something that was completely unique, that had never been done before, in this conversation. And so, like, the whole story, I think, is pretty dope.
Yeah, it's
Yeah,
awesome. Mike, when are you going to write a book? My Journey into Flat Earth, available on Amazon?
fourth book. Yeah, I'd like to say that we've all been here for I don't know how many years you guys have been in this. I've been like since 4, but like I've never come up with my own method, my own proof, my own detail. Then Mike came in, joined all at once, same month, first week, plopped down the table. He said, "What do you guys think of this?" We're like, "What?
Yeah.
Oh shit!" So putting us all to shame. I love it. I guess that's what happens when you convert with a full PhD or whatever. You got prepared.
Yo, we should actually do that. We should put a book out that has it's like just a whole bunch of flat earthers journeys, but concise.
It's one story, bro. Everybody's got the same fucking story. Yo, I was finna prove this shit was dumb as fuck. Everybody's got the same fucking story.
That's pretty
There's
much it.
only
Yeah.
one story, bro. I swear to God, it's only
I
one.
was trying to prove it without assuming it first. And then
Fact.
that's it.
Dude,
It's over.
the only difference is how honest you are with yourself as you're doing it, right? That determines who ends up where we are and who ends up an anti-flat earther or whatever.
Yeah.
Mhm.
Yeah, but, oh,
I heard
Coffee showed up. What's
Eratosthenes
up,
made a
Coffee?
comeback today, Shane.
Yeah, coffee and real.
You mean Coffee the Flat Earther? I heard, or
Hey, Coffee, you wanna tell him where you at with it now, bro?
I got your sweater, homie.
Coffee the bully, the FE bully. Tell him, Coffee.
Yeah, so what I've got, because I missed most of it, I fell asleep earlier, so I missed most of the presentation today. But basically where I'm at with it, it seems to me like you guys have an issue. Like the experiment at face value for me doesn't prove flat Earth, right? It's not a win in the bag for flat Earth. What it looked like to me is that this experiment helps to highlight any inconsistencies with the values we use for refraction.
Okay, so
Right.
what about everything being based on the model and the laser tests and the visual tests and the bottom up obstruction and the motion of the stars? What about all these things combined with this?
Yeah, you have a
I'll
leg
be
to
right back.
stand on, but you guys haven't conclusively debunked it. Right? It's still an argument off of the subtle lack that we don't agree on the values of refraction, and no one has proved, at least on your side, how those values are misapplied with any
Yeah.
corroboration or consistency.
So So I did specifically earlier when I showed the relationship of true position and apparent position with respect to the peak and how the intersection difference is, really small. It's usually it's been as low as in the arc seconds range. And then when we get into the scenarios where the globe needs a miraculous number of refraction, it'll be triple or double the amount of terrestrial drop. Like, so it's like we conclusively showed that because the occlusions are physical. So when that happens, there's not going to be this crazy amount of 10 plus arc minute difference in position. And in one of the measurements specifically, there's a 40 arc minute difference in position, which is preposterous because it's purported that the star would be beneath the globe. So if that doesn't falsify it, then nothing will. But I'll be right back. I got to go to the bathroom.
Yeah, it still sounds like it's built on your agreement with our values of refraction. And I mean, arguing with us up here to build a streamline to debunk it is cool. But, until there's an application or a prediction that can actually throw it in the bag, I think it's a good starting point. You feel me? You guys came up with a way to find out an inconsistency in, our refractive values. So use it and, create a prediction that we could actually predict.
Dude, the only consistency was how wrong, however you want to use refraction is. We allowed for all refraction, terrestrial, celestial, whatever you want to do. We added, everyone had their own custom. You can add 2 arc seconds per kilometer to exonerate the ratio of 7/6 R per kilometer. We allowed for everything and none of it worked. So for you to just say it's all about the different refraction, it means that like what? What, Coffee?
He came
I
in
mean, then
abracadabra.
listen, then prove it with a method that takes out all refractions and then explain your own characteristics of whatever optical phenomena is going on in our view. But until then, we're still at square one arguing about refraction.
What about all of the FE proofs plus the radiation background, the how that's poking holes in the Big Bang theory, and how gravity hasn't been discovered. What about what about all these things combined? Still no, just a leg to stand on.
Bro, you guys need a this is the point that I was trying to point out earlier. You guys need conclusive unity. You feel me? Because everyone has their own individual. I mean, you guys are.
I know.
You see, my bad. Let me just
I
finish
feel
real
you.
quick.
We gonna
I'll
get to
try to
that.
hang it
That's
up real
why
quick.
I've been challenging like everyone to try to put together a model of the surface. That's why I put that challenge out there. So hopefully we can work on something like that in the future and get that done. I feel you on that.
Yo, the real sacred is here. Someone give him a mic. I want to see if he's still real. But
I shot him an invite a while ago. I'll shoot him another one.
all right, maybe he's just listening.
Who we talking about?
Oh boy, sacred.
Oh, man, Sacred don't want to come up, man. He moving around. He typing in the chat.
Yo, Sacred, get up here, bro.
That's what I said.
What are you doing down here, not up here
He's
with
been
the
down there
boys?
for quite a while.
Yeah,
And
he's been
I've
at it.
been meaning to
bro?
say hi for a while. No, he's been there for like half an hour at least, man.
Yep.
Well, let's play the game where you put the spotlight on him and make him uncomfortable enough to accept the mic. What do you guys think?
You in, Blue? Get in here.
No, he's having too much fun tearing Teddy a new asshole over in that.
Oh, dude, that Teddy guy said earlier that the measurement alone of watching a star move proves that the Earth is rotating. I was like, I'll say
Yeah.
that looks like a good time to diverge into kinematics and dynamics.
Yep.
But
Exactly. The Kenya equivalent speech. Here we go. Roll it.
It's like an equatorial mount proves that the Earth is moving. It's like, no, observably, empirically, not that. Like the opposite of that. Doesn't do anything about dynamics, but that's a really funny sound.
oh shoot.
Busted.
We can't swear, but we can smoke bongs or whatever. It's fine. I get the rules now.
Water.
What was Coffee saying? I'm sorry. What was his argument? It was after there were all types of refraction are
It
equal.
was inconclusive, even though we went over the refraction and like it basically cancels out or triple cancels out Earth curvature, and then in the measurements where the true position and the apparent position are very close to the peak, they intersect and it's no longer visible, and the difference in between them is very small. But in these examples where the refraction correction is 3 times, 2 times, or equal to the amount, that value goes up a bunch. So, when we look at things that are conclusive and whatnot, it's not like that we're disagreeing with refraction. We're saying that, like, physically, mechanistically, that the measurements that were asserted previously that only prove the globe work on the principle of the intersection between the peak and the true position. Otherwise, they wouldn't work at all. And when we go to peaks where that's where the refraction difference and the drop are there's like a significant difference, we can see the difference between the two models here. And if we were to play a game called like for $5,000, can you backwards derive my location based on or closely approximate my location based on occlusion timing and known elevation to a peak? It's like if you were to play that game and you have $5,000 on the line, would you use the globe math or would you use plain trig?
Yeah, you can use either or. It's just if you're accounting for
Nah.
refraction and curvature drop. Now, if you want to say the refractive values that we're using are off, all right to it. You feel me? But you got to conclusively prove it
Yo,
first. This is a good
coffee,
starting point to
Coffee,
conclusively
coffee,
prove it.
coffee.
coffee.
But
Five
this is
Can I
thousand
not
say
dollars.
something?
the
Coffee,
nail on the head.
coffee. $5,000 on the line if someone were to offer you, and you had to make a prediction of how close you can get to the observer's actual distance, and the only thing the person was going to give you was an occlusion angle and a mountain elevation. What math would you use to try and get that money?
Which angle would you pick?
No,
I don't see
not
the prevalence of the question when the issue is the refraction. I don't see it.
Prevalence? Oh my fucking
Wait
god.
here,
well,
coffee. Coffee. I want to explain something to Coffee because yesterday we went through something and you were completely misunderstanding the distance in the right angle triangle compared to the hypotenuse. And so right now what you are misunderstanding here is that the amount of refraction is only coming into play when you are dealing with Earth curvature drop that's about the same amount. And when those two are canceling out, that's when globe angles, when it's saying globe, like more globe than flat Earth. So what you're missing here is that when we have a large distinction between what the flat Earth and the globe Earth angle should be, there's no issue with refraction. It is significantly showing towards the globe or the flat Earth side. It's only when there's a small distance and you've got that globe drop and then you've got the refraction to bring it back up, or double or triple the size in some cases. So you are totally misunderstanding how refraction is coming into play in these experiments, in these situations. Just like you were completely misunderstanding the distance and how to derive the angle from the mountain peak yesterday. Because you thought there was a rise over run to get that angle to the star from the mountain peak, and that had nothing to do with it. That's why you are completely misunderstanding how
No,
refraction is
it's still
coming
a
into
rise over
play
run.
here.
It's just stellarium doesn't use it to plot any distance. That was the breakdown, and you proved that stellarium doesn't use distance.
Correct. You were trying to say that they were changing the distance in rise over run to get the angle, but you completely misunderstood the argument and didn't know that from the mountain peak, the angle from the mountain peak was just the angle up off the horizon. From Stellarium, how far is that star up off the horizon?
No, you
Like,
misquoted me
that is
again. So when I attributed the distance, right, I was doing a geometric connection, but I was trying to wrongly attribute distance as if it was this.
right. You thought they were changing the distance. Thought they were changing the variable in the rise over run equation. That's what you kept claiming, that the variable was being changed, and you can't change that because you thought the distance in the rise over run was being changed because we moved from the observation to the peak of the mountain. Because you thought once we went to the peak of the mountain, our distance changes, so our rise over run would change. So there should be a different angle from the mountain, is exactly what you explained to me, and how I explained to you that there was no rise over run equation to get the angle from the top of that mountain peak.
Yeah, no, you were misconstruing me. So when my issue with the distance in their calculation was for the back calculation to get back to the distance. I was saying for the globe side, if you used every variable correct that you used for the forward calculation, you should get back to your distance. The only way you shouldn't get back to the distance is if you took a misstep.
No, using a refracted angle. That's all it is.
No. 1 second. I'll comment on that in a second. I got a thing I'm doing real quick. But you're mostly right, Coffee. Give me 1 sec.
But you specifically yesterday were trying to tell me that because we moved from Mike's house to the mountain peak, that the distance changed, that we were changing a variable because that distance would have changed. But that distance, that was like the hypotenuse side of
Yeah.
our right angle triangle when we moved from the house to the mountain peak. And that wasn't even included in what you would do rise over run. So there was something you were very mixed up about as far as that distance changing, because you thought that that would create a new triangle, a new rise over run when you got from the mountain peak. That's
All right.
exactly what it came down to.
So Coffee, uh, at the beginning of the Prezi, I think you said you came in at the midpoint or something. So you might have missed this part, but I did have a circular loop in the math for the distance derivation, because if you use the occlusion angle based off of the distance to the uh, to the peak, it when you as to get the altitude, if you derive a distance based off of that altitude, it's always going to go back to the distance because it started with that distance, so it's going to be circular. So if you increase the angle to, like, way over what it would predict, it still cancels out and comes out to be exactly the observer distance. So that was circular in that, but that's been corrected since then to where it pulls from the only known variable, our control, which is our delta altitude, which is always going to be the same. So we do the occlusion, we take the delta altitude and we do the tangent of that times the occlusion angle, and then we get that for our distance now. So now the flat Earth no longer matches every time exactly or whatever. It's an actual, like, comparison to what it would be with respect to the one known variable. So
But that's not what he's saying. He's saying the Ruhif method, that when I get to add it to get my prediction, I get to subtract it when I do my elevation and distance.
So he said, like, multiple things over the last time that we talked or whatever, and right now. But right now specifically, he's talking about the distance relationship from the last time we spoke when we said that we could derive it exactly. He was saying that it's circular. He kind of, like, um, misspoke a little bit on describing it, but what he said wasn't entirely wrong. So if you do that with a different triangle, it's going to give a different distance. So the globe would never win in that scenario, and we would always be exact. So the reason, that's the reason that we changed it to go off of the control variable, the elevation difference now. So it is actually. So when I asked earlier about, like suppose you were on a game show and you were going to win $5,000 if you could derive the close approximation to your distance, and all they gave you was an angle and an elevation. What would you use, plane trig, or would you use like a globe drop estimation? Because they're going to get two different outcomes. They're not always going to be close. There's a chance you might win if the refraction was equal to twice or triple the amount of globe drop. You would, there's a chance you would win depending on the distance. So, but what we're looking at here is like consistently when the refraction doesn't compensate for it, flat Earth wins, like by a pretty good margin. If I were on the game show, I would choose plane trig.
I'd pick plain trig too, especially if there's money. Who'd want to say no to free money? You just have to pick the right angle.
Yeah, no, the angles are always predicated on your controlled variables. You feel me? Until you predict something using that predication, then it's pointless. Because all we do, you gotta understand, right? At least from my standpoint, Mike is observing the occlusion timing, right? A globe earther could do without the proof of the invalidation of our values of refraction. A globe earther could observe this occlusion,
What the fuck did he just
right?
say, dude?
Get all the controlled variables and just flux the refractive value. At least that's what you guys have been accusing us of, just to hide the curvature drop and match the angular height to that occlusion time.
What the
Well,
fuck?
I'm not so much as accusing you of it, but rather I will inform you that computationally, the refraction coefficients derived, the input of them is Earth's radius. So based off of the angle that you input, it moves it to wherever it has to be a globe. And so I know, you didn't do it, right? Like it's not your fault. But the reason that relationship exists where it's either equal to or it doubles or it triples is because it's empirically derived off of a curve fit to make it appear like the Earth isn't flat. So there's that aspect of it. And in addition to that, you also have to consider the when you apply just your raw angle that you're looking at to celestial refraction, you get where the globe, quote unquote, predicts the apparent position should be. And all you did was enter a straight angle from to the horizon. That's what celestial navigation is based off of. So like the fact that the curve fit works in such a way that the formulas are such that you can just go out to the horizon, get your elevation to the star, raw, flat Earth, you don't have to make any drop adjustments over any distance or anything crazy. It just based off of the angle, the coefficient will adjust it to where it needs to be for the globe. So like that's also pretty revealing through this analysis as well. So
No, I've
because like
seen that's what popped out after I had my conversation back and forth with Kat. It helped me realize, like, maybe going about this the geometric route is wrong, because I don't personally, to me, I don't really see anything wrong geometrically, because we're not making a prediction. All I see is, you feel me, an argument between the value within the controlled variable, which is the refraction.
No, you're specifically making a geometric prediction.
no,
And
you're the controlled variable isn't the refraction. That will change. Like it's not it. So what we have, right, is we have the elevation between us. We have a distance that'll change, and we have the occlusion timing. So the only thing that we're referencing there is the altitude, which is our controlled variable. The independent variable is just the occlusion angle. And when I compare all of these, right, there's no, like the flat, I'm telling you, globe Earth is off, and we can see the differences in each mountain peak specifically. And what I've noticed is that when there's a certain expected amount of geometric globe drop, refraction comes in to be equal to or double or triple the amount, just to be, which is equivalent to saying, well, it just looks flat, but it's a globe. And to do the inverse, right? Suppose you did a reciprocal zenith measurement or something and said, look, it's a globe, and I said, no, it just looks that way because it's flat. Like you would be like, you would be like, what do you mean? That doesn't make any sense. So when you say like, anyway, when we derive the distances and everything based off of this information, when you say like we're not making a prediction, well, if you were to try and predict your distance off of that, would you use flat Earth or globe Earth to get closer? Like the purpose here is to analyze your guys' model and show which represents reality best. And we can plain trig the distances back, no problem. When we get into results that quote unquote prove the globe, they don't actually prove the globe. There's just no distinction between the two models because of the refraction correct applied to the position of the star and the true position of the star. Like, it's very obvious in the data. I think you should like look at it, man. Take some time with it, because and you'll see your argument's kind of like it doesn't, it's not supported by the measurements.
So can someone highlight the prediction made in this experiment?
Yeah, predicting my distance. I'm predicting which one of these models gets closer to the distance of the observer.
But that's post hoc, right? When he formulated the experiment, that was controlled.
No, just which one of these models gets closer to where the observer is at. Which one can predict the observer from that geometric relationship of the occlusion timing using the true position or the refracted position at observer location? Which one of these gets closer to the actual position? That's the whole thing. If you can't predict where the observer's at, then that's it. If you don't accept that premise, then I tip my hat to you, good sir.
Yeah, no, I'm just guessing that it's down to a bunch of hat tipping because I don't see anything conclusive here. No one's proved anything conclusive. No one. I mean, you say the prediction is where the observer's location is, but that's a shared constant. The globe Earth has the 50.7 kilometers. The flat Earth has the 50.7 kilometers. So I don't see any reason for that to change in any forward or backwards calculation.
So listen, the reason it changes, right, is because we're using the delta altitude of the mountain in between us as our constant. So that's always going to be the same. So when we do the trig with the apparent position and the true position, we're going to get two different distances based off of that, because the only thing that we used to start with was the known value of the elevation. So the distance is going to be completely independent based off of the angle that we use.
Maybe you should define apparent and true position.
Yeah, okay, so the true position is not the position of the star that you see. It's a calculated position based on where the star once was on the vernal equinox when they took a zenith measurement of the star. And then they just added 15 degrees per hour to that to use that as the baseline for predictions of where the star is going to be so that they could, relate that to a position on the ground based on time in the future. So that's just a calculated position based off of where the star once was. The apparent position is the position of the star that you actually see. So if you were to think about it in terms of suppose the star is has like a physical light source, like a flashlight, and the flashlight is always going to be moving a little faster than the light that it's casting behind it, because it has to go through a medium, it's refracted or what have you, and it's never going to be at the exact one-to-one location as the apparent position. So we're referencing this calculated true position of what you could consider the light source if there was one, right? And that's what we're referencing. And so when that position lines up at the time that the star is no longer visible, we reference whatever that angle is, and that's in reference to when it's in line with the peak. So if we're on, so suppose we're on the peak, and the angle is 231. Well, if when that star's calculated true position is at 231, if that just happens to be like when the star wasn't visible, and then from that, because we know where we're at on the globe and all that, we can go into stellarium and we could look at where the star was at that time of occlusion with refraction on for the observer, so we can get their apparent position. So now we have two different angles derived from real observations where the star was at that time, and then we can derive the angle off of the tangent of the altitude difference. So we get two separate distances based off of the same method, referencing two different things. One is a system that references plane trigonometry based off of physical intersections. The other is it's doing plane trigonometry based off of the apparent position angle. So
Yeah,
we so
so
so, so we get two different distance outcomes based on that.
yeah, I
So
don't get why you think your method is appropriate. All you should need is the apparent height above the horizon of the star, right? You line that up with the mountain peak. I think that's 2.23 kilometers, given the observer's height.
2.3 kilometers.
Pretty sure
I'm
it's
not.
Yeah,
degrees,
so you
not
take a
kilometers.
I'm not sure what you mean. 2.3 degrees, though. Yeah.
no, hold on. Let me go back to my
So
work real quick, because if I'm not mistaken, you got to subtract the observer height from the total height of the mountain, right?
yes. 4,300 minus 2073, and from that you get
Yeah, the
27.
leftover that up to that is the 2.3, right?
It's 2,227 is what it comes out to. That's the difference in altitude between you and the mountain peak.
Oh yeah, so round it off to about 2.3.
Well, I'm not. Oh, like are you saying
Yeah,
230,
2.27. You round that up to 2.3.
220? Sure.
So
Okay.
he's just talking about the rise.
Sure.
Yeah, so I don't get why you need the true position of the star. Wouldn't that change the perceived altitude?
No, but it would change the distance derivation that you get out of it, because what we're referencing is where those things are when the star is no longer visible, and we just go, hey, what do these angles happen to be? And if I use them, does one of them go back to my distance? And if so, like how close?
Yeah, but you guys use the shear constant of the distance to set the elevation angle for the
No,
observer.
no, nope. We only
Nope.
we're
And I
Is
only
the
cleared that up
distance
with you
not a controlled
yesterday, Coffee.
variable?
no,
We
we
cleared
only
this
need
up yesterday.
we
Yeah,
only
no,
need
and the issue was I was attributed to distance of the star. But if you move away from a star's zenith, it declines in your field of view according to your latitude. So we know stars go down in your field of view with distance. That's
yeah,
understood.
coffee. That's exactly why I'm using where the star's apparent position was at that time.
Yeah, I don't know why you're using the star's true position though. That's what I'm trying to figure out here.
Because that's when the intersection happens. So let's say hypothetically that the Earth's flat and that mountain peak appears to be 217 or 219, but really in reality it's actually 230. So what we want to know is, suppose there's a light source to the stars, and what known as the true position. What if that light source was at that same angle at that same time? Like what would happen? And suddenly the star is no longer visible. but the apparent position at 217. So that's why we're using that relationship. We're just seeing what would happen, and what happens is we can create a triangle that is parallel to the ground and the stars, and with that we can derive or closely approximate our distance way better than what you can do if you use the 217 globular angle.
I
And if
hear
you,
you, but
and if you try to use the apparent angle with uh, on the globe position, it's astronomically off. That's what the if you go to the if you look at the spreadsheet there and you see the mu Heffron and then you see like mu GE, that's represented by deriving it from the true position at observer location in the same way that we're using the true position at observer location. And it's for the peak. So it's, there's no only one of these triangles, you know, like the implication is that the that geometric relationship shouldn't exist. There should be no reason why the star gets occluded when it's physically intersected by a mountain peak at an elevation that it isn't predicted to be at.
yeah, I get that. But you got to understand, right? When you're observing a mountain peak, right, and you're watching the star occlusion and labeling it at 231, that's predicated on the fact that you're not considering globe refraction and globe drop. If you consider globe refraction and globe drop, the observation doesn't stay 231. It becomes 219, right? Not the timing itself, because we never predicted the timing. So we don't know if the timing matches unless we calculate an occlusion timing and go outside and see if that occlusion timing matches.
All you have to do to calculate an occlusion time is know what angle it got occluded at, because angle equals time.
No,
So that's
I get that, but if I'm observing
so
the angle, right? With
hold on a second. You
go
often
ahead, go ahead,
say
bro.
I get that and then go on to say things that show that you do not get it, because angle equals time. So that is the you don't need to do that. I mean, you could, but it would just be unnecessary steps, but they're equivalent, so you don't need to do that. Now, when you say you haven't accounted for globe drop, I have. That's why I'm using 222, the apparent position where it was occluded, and that gives it different distance triangle than what the true position at the peak intersection does. And I know this relationship is meaningful and true because when Jesse went out to go take measurements where the intersection point would be ambiguous between the two, he the star was no longer visible. So within 4 arc minutes. So I know that my premise is solid. I know that it physically works that way, and I can even point to another example that was done by me where that intersection same relationship occurs. So I know that when the star's true position is lined up with that peak or within at least 4 arc minutes of it, it's no longer going to be visible. I have a whole that's what this whole spreadsheet
How do
represents.
we know if we never calculated the timing and just went outside to look to see if it occludes?
That's what we have video footage of, brother. That's the whole purpose of this. We know when it
Yeah, but
occluded.
that's
We
not a
have video of
predicted
it,
timing. That's just going outside to
bro.
actually see what time the
Bro,
star occludes.
listen,
That's not
listen.
predicted calculating using your
Earlier,
angular height, a timing.
earlier,
Hold on,
earlier.
let me finish, my brother. I got you. I'll
Uh,
let you finish earlier. I got you.
all right, go ahead.
So if I'm looking at this observation, right, the star occluding, right? You're saying if I use flat Earth math that I could come up with 231.
Yes,
Correct or incorrect, right? Now, a
yes. That
globe earther is saying that if I account for the variables of curvature drop and refraction, I get 219.
is,
How do I verify who's correct without predicting an occlusion timing? We already saw the occlusion.
listen, the occlusion time equals the angle. We know when it's occluded that at that point, at whatever that means, the star was no longer visible. So when that star was no longer visible, we just go, hey, what did that angle happen to be? The time and angle relationship are the same. What we can do after the fact is derive distances based off of that and figure out which model is closely gets represented. Now, when you said who's more correct, 217 or 219 or whatever, I agree. That's why I incorporated this specifically where I could make this 219 if I wanted to right now, but I'm not even going to do that. But here, check this out. I do the math on what it would be for 217. I'm going to do what it's going to be for 219, and I'm also currently doing it based off of where the star actually was, which is at 222 for that position.
But since the angular height is tied to the timing, can we use both timings to calculate? I mean, use both angular heights to calculate the occlusion timing.
Yes, that's what we did.
Yeah, I'm talking about clock time. So you know how the
Coffee,
star
angle
occludes at
equals time, bro.
18:27:52? Can we
Yes,
calculate the same variance of a clock time and see if it matches with the 18:57:52?
coffee. If angle equals time, and we use occlusion time to confirm the angle, and the plane trig angle is 231, and the occlusion time was 234, and the globe predicts 222 or 219 or 217, depending on who you ask. And for the observer on the ground at that time, the actual occlusion was 222. What exactly is your contention? I've accounted specifically
Yeah,
for all
yeah,
possible
you're
gloss.
not accounting for clock time, my brother. You're giving me angular heights. I could skew that for the globe
Clock
model with
time is when the
curvature drop
star
and
was
refraction.
occluded.
So until I could calculate that until a clock time and predict that clock time, then what is the point?
Coffee. You can absolutely do that. It's just a more complicated math equation. It's just, you know that Stellarium does local hour angle transformation? I can give you the equations for it from one of Mike's PDFs that he does because his spreadsheet does that. It's not necessary for me to computate the local hour angle transformation timing for it. I can just use the angle that it was occluded at because angle equals time. You said earlier, yeah, I get that. But then here we are running into a scenario where we have the time because we have the angle. And you're like, I need the time though. But time equals angle. Like, but you want me to do this idea? You want me to do the local hour transformation? Like that's like I'm not gonna like I don't care about that. If that's your contention, then like your contention's noted. And
For the globe model,
I have all the
my bad.
globe
Go ahead.
angles possible. I have all the globe angles represented, and none of them help. Like, does that Matt? Does that
But is those globe angles not predicated upon curvature drop and refraction? So if I take those out, right, that occlusion timing observed, right, that angular height is going to be different.
No, it's gonna be what it is at the observer time, bro. You can't change
Bro,
the time.
the observer time is where you observe it, right? The angular height is what you use to control variables to calculate. Am I bugging?
Yes, we make two different predictions on when
When were you not?
the star is no longer going to be seen. You are bugging.
So did we do that here? Did we come up with two different times and
Yes,
just go outside and see if it included at that time?
Why do you keep talking about a different time?
that's
There's only
coffee.
one time.
Because that's the
Coffee.
best way to
There's
check your
coffee.
work.
Coffee. The globe angle time is the different time. That's why it's in like, bro. The, when I reference the position of the observer's apparent, like when they're looking at the star from their location, like what the globe predicts, right? That's exactly what you want. Like what you're asking for is that. And
Yep.
that angle is in there. It's represented in there by 222. Because that's when the star that's the same time that the
Yeah,
star
my
wasn't
brother,
visible for the observer on the ground.
but you're telling me this after the observation, right?
Hold
So
on.
obvious.
I
Oh,
have a question.
that's completely irrelevant.
The timing is coming from Stellarium, correct?
What's that?
The time, the verification time comes from Stellarium.
Yep.
Okay. Does Stellarium have a you can go future to in Stellarium or no?
Yep. Yeah.
So can we just I mean, because he's just saying you're giving this first instead of doing it the opposite way. Can't you just go into Stellarium and pick a future date and then go watch for it and
You
see
could
if it matches
totally
up
you
and that
could
wouldn't that
totally
be a
do that.
prediction?
You could totally do that, but that's how we originally were presenting it, but that's
Hmm.
complicated. People don't get that. What the only thing we really need to do, right? Because think about what we're doing, right? At the end of the day, we go, okay, there's a mountain peak. What's the angle flat Earth? What's the angle globe Earth? So we've already got angles. Angles correspond to time. And then
Right.
we're just like, when the star is not visible, what angles what angle was the true position at the peak and what angle was the apparent position for the observer? And then we just start doing triangles off of that. It's literally as simple as that.
Right. So Coffee, what you could do is you could go into Stellarium and do the future version of the experiment using the same, he's got the spreadsheet there.
That's actually. Oh, I'm sorry. Sorry to interrupt. That's actually what Goose did. Goose did that because he did a named
Uh-huh.
star. He did Regulus on Varley SE2 Squamish. So he actually plotted that out because it's a named star. He wanted,
Hmm.
Anyway, yeah, he did exactly that. Like you can do this. Like
So
it's not the angle's the angle, bro.
Coffee, it does have predictive power essentially.
And
Yeah, but
and
not the way it
and
was
and oh,
formulated.
no
That's
no
the
no
point.
no no, it does, because think about this, Coffee. You can go into Stellarium to predict when the occlusion timing is going to be. You can play it out when it's going to be at that angle, the true positions at that angle, and then from your distance, uh it just all of a sudden the star is no longer visible. It's directly predictable because we never told Stellarium where we were truly at. That's why we get into these distance comparison based off of just the elevation and the occlusion timing, because the occlusion timings are independent variables. So you have an occlusion timing for the apparent position at the observer location. We have our timing or we have our angle for the apparent position with respect to the peak's location, and so those are two different independent angles, and we're saying what distance do we get out of those, and flat Earth is closer every time except for the
Yeah, but that's
instance
not
of
the
a couple of others.
initial formulated experiment. I'm talking about the way Mike's experiment is
Bro,
formulated. It doesn't solve anything. It just gives you a
bro.
starting ground. I get your backwards calculations and everything ad hoc that you're doing, right? For
It's
the
my buddy did it post hoc though. That's what you're not understanding, is that you don't need to do that. It's already in it, you're already able to do it because it's equivalent. So
yeah, I just
so
noticed
so
I was
so
saying
so
ad
so
hoc and not post hoc. My bad, y'all.
so the real thing though is, remember, we can do it without telling Stellarium where we're at, and we can more closely approximate our location. So
Right.
that's the huge significant difference there, and we closely predict the elevation of the mountain peak as well, except in the instances where the refraction thing comes into play. But when we're off, we're not off by like a drastic crazy amount. Like the globe is off when it's off. When there's an
Yeah,
actual
but if
difference.
the globe person doing the modeling the same way you're doing it, just flex the refractive values, they could get it to match, and then say that they just used a different weather model.
No, but then what you'll see
Nah,
is
that
you'll
doesn't even
have
make
like the
sense,
under
bro.
or over.
That doesn't even make sense. The star,
Yeah.
we know where the star was at. That's the whole point of using Stellarium to check, because we can check the measurement. We can check it against where it's at. So there's no fudging. There's no thing. The triangle is the triangle.
And it works pre or post.
It works
And
pre
they
or post.
can't
Stellarium
take
changes its
they
output
can't take
depending on
Pike's
what you
peak
check. What
measurement and fudge it to get it right. That's where you're misunderstanding, Coffee. They can't take the measurement of Pike's peak and take their refraction and their variables and fudge it up to make it right. That's where you are misunderstanding. Is that is not possible. That is not happening on
does the
those 7 peaks. There is no way that you can fudge the numbers to get that globe angle up to where that star was refracted. You're not fudging it that far. That is what you are misunderstanding on how these variables are being applied. Just like I said earlier, that you need to go take a closer look at what is actually going on here, because yesterday you completely misunderstood stuff and you are completely misunderstanding stuff today, because they are not taking globe refraction and globe drop, and they're not taking all of their variables and being able to fudge stuff to move that angle up to where that star is being refracted on all of these major mountain peaks where there is a significant distance and a significant difference between what globe and flat predict. You can't fudge
I
to get
mean,
up there. So you're misunderstanding.
John's model matched. He just used a different weather model. He used 4.1 arc
What?
minutes of refraction for the celestial, and then I think 1.7 for the terrestrial. It's just a different refractive
John's
value, but his match.
John's observation was at sea level. It was at a close distance and a short hill. So he was
Listen.
at one of those special places where globe
No,
drop and
no.
angular refraction cancel each other out.
Is
Because you're so
John?
close there.
What was
Yeah, I think
John's?
it. I think it.
Is he the one that did the 1 kilometer one, the 1
Yes,
mile?
the observation on the
Dude, so
hill, that was John's.
coffee. The sky moves at 30 meters a second. The globe drop over 1 mile is 8 inches. The difference in predictions on that is ridiculous. It's a misuse, dude.
Yeah, but if he got it to match, you feel me? All that matters is flexing the variables. You guys are complaining
No,
that it's not a use here,
It
but
matches.
no, you can't flex
No,
the
I'm
variable. This is what you
explaining
were
to
just
you why
doing.
it matches, because there's no difference in prediction there.
Right.
hold on, hold on, hold on.
At
What
that
are we
distance.
talking? I'm talking about John's calculation for the Pikes Peak model. I think y'all talking about an actual observation.
Dude, what? Okay, listen.
Yeah, I'm talking about
Listen,
John's calculation
coffee.
for the Pikes Peak observation.
Okay, coffee. I have calculations for 217, 219, 222. I can make the angle whatever angle you want, and it's going to
That's
give a
exactly my
value.
point. That's exactly my. You can make it
Stop.
whatever we want. How do we check it?
Stop. Because we know the angle that it was actually occluded at, and that's 222, and that's also the one that I reference. That's the actual position of where it was at
Bro,
when it
but
got
if
occluded for an observer
at
on the ground.
222, right? That is a
Yes.
measurement, right? Based on your controlled variable. So if you change those
Based
variables,
off
that
of our
measurement does.
independent variable, because it would be based off of our distance location, because we're at the observer location. But dude, it's giving us an independent variable because it's an angle there. But dude, like you're
The angle can't be independent.
coffee. What angle do you want me to use?
It
What's the
doesn't
angle?
matter what angle you use. That's the point.
Okay, dude. Okay, dude. If it
It
doesn't
makes.
matter, you can't prove anything. Then, I tip my hat to you. Good day.
Yeah, it's unfalsifiable because all it goes
You
by
don't
is
You are
the
making it
understand
variables
what's
that you
going on,
use.
unfalsifiable, though,
Coffee, by
dude.
what you're saying.
Bro,
You
you're
don't
making it
understand.
unfalsifiable. There's only the angle that it actually was at when it was occluded. So I'm
Right.
using that. I'm telling you, if you're not happy with that, I could make it whatever you want, but it's not gonna help. And then you're turning that into, yeah, that must mean it's into like no, dude, you're completely just like, have a good day, man.
I
I
mean,
don't know
Alan,
what else
how
to do.
did you measure? How did you get the 231 output?
I calculated it based off of the distance and the elevation of the mountain difference between us.
All right. So when you make the observation, do you have to take these things into a consideration when figuring out at what angular height this occlusion was observed at?
No, we only have to just record the time in which we no longer see the star.
So how do you know it's at 231 minus the time?
Because time equals angles, and we can go into Stellarium and look up where the star was at that time.
Yes, but when we look at stellarium, we use stellarium using the globe modifications, you get 219. This is my
Yeah,
point. So how do we
yeah.
figure out which one is right?
Well, coffee. Here's what we do. We derive distances and elevations based off of occlusion timing and the known elevation so we can compare which one's right. That's the whole purpose of this, big dog.
Right.
I
You
mean,
just
both elevations are
And
based
that is
on
what I
either.
went over with you at nauseum yesterday. Over and over again, I went over
It
that with
just
you.
no, I get that, Cat. We got that, babes. My bad, love. but it's too arbitrary. What does it
Nah.
No,
prove?
it's not. It's one or the
All
other.
right, dude.
It's
Yo,
one
it's
or
not
the other. You
arbitrary
just
though.
walked into it.
Dude, it's not like so now it's arbitrary. Like, dude, I mean, if that's your position, your contention's noted.
This guy just says things.
Yep.
Right, because it all depends on the variables. That's how you get your angular height.
It
So if
depends on
if I'm
bro.
observing the star, right, at 219 and you observing it at 231 and you're telling me you're back deriving the distance using all these controlled variables, you're not getting back to the same distance. So it has to be that you're changing the
No.
altitude, obviously. So
Bro,
it's
Oh,
like,
coffee. I'm using the independent variable of the occlusion angle, and I'm using the control variable of the altitude difference between us. That's why, and then so the reference that I'm making is the peak to star relationship. The reference that the globe would like us to do is observer to peak relationship. And when we use those, we get two different results for distances and elevation to the peak.
yeah, I think the fact that you're using the angular height as your independent variable is what's, I think, fuck you up here.
so this is what's gonna have to happen, Cup. You're gonna have to just go do this yourself, bro, and then show everybody that your way is right, because everybody is saying that your way is not right.
Wait, this is what we gotta do. We gotta do. Explain
That's what they're supposed to
exactly
do.
what's arbitrary.
The angular height is arbitrary because it's dependent on the variable factors of either the globe or the
If it's
flat Earth.
dependent upon something, then that's the antithesis of arbitrary.
Yeah, man,
It's,
but that's
it
not
gives
prevalent.
it gives mutually exclusive outcomes. That's the whole
Yeah,
purpose of testing.
there's two different things, bro. Which one is right? Exactly.
It's specifically not arbitrary.
Yes, and without a actual prediction, it's
Shut up.
arbitrary.
Dude, so
It
he's saying
doesn't
it's based
matter.
on this very specific thing, so it's arbitrary. This is the most
Yo, and not
retarded thing
only
I've ever
that,
heard.
It changed cut out for everybody else too?
Yeah, it's quiet.
Yeah. Dead air. Oh man, there's more people in here. Oh, we got Disjar. Mister's here. Tay Tay.
He dropped down from Twitter, it looks like, too. So Alan's is still up on Twitter.
James is saying thanks for tuning in. And
So Alan's is still up on Twitter.
oh, sorry about that.
He dipped.
Oh, somebody's saying they can't hear Alan. But Coffee's lost his damn mind. He's all, your calculations aren't predicated on Earth curvature.
stillman his argument.
Yikes. Ooh wee.
Is that
Ooh.
straight for 10K?
I laid it out for you like 10 times yesterday when we talked copy in like layman's
Oh, you
terms.
guys think
I
I'm
laid
supposed
it
to
out. So
apply a still man because you asked? That's what we're thinking here.
Well, no, it's just kind of stupid for us to sit here and pretend that you're going to refute something you're incapable of even understanding. So if you want to stillman it, then maybe we could even like know you understand it.
If you didn't feel like understand it, then you guys shouldn't have the conversation to begin with. I'm not going to
Nice
continue a
avoidance.
conversation with someone who doesn't understand something.
Do you
That's
think you
what he
could
just said.
stillman? Do you think you could stillman it, meaning like pretend to be a flat earther and stillman this argument as to how it refutes the globe?
Yeah, I don't think it does.
That's a
Nice
no.
still, man.
Not able.
Ouch.
that's sad because I said it to you so many times yesterday during our conversation, and you didn't listen to anything I said or how I explained this experiment or how I was talking about how the right angle of the rise over the run, how that worked, how there was a different angle from the observer, from the mountain peak. Like coffee, you even came back and you apologized for being wrong about how Stellarium calculated the angle. And you even said that I could go tell Alan, yeah, tell Alan you cooked coffee today.
But
So you
to be
were
fair,
extremely wrong.
Kat, I did also mention that I had just I had just had an extensive back and forth with Coffee, and I thought that I understood his position, and then he just circled back around, and then I reneged, and I do not understand his position. So I mean, I thought I got through to him too at one point, and then that just went away.
Bro,
And
this
he
guy
got to
just
cut
hit
it
us with
off.
the classic,
Oh, it
bro.
seemed to change.
Can we
I
just
mean,
be
I
blunt
didn't really
here?
understand it yesterday at all, but we got down to it. And, he was telling me that changing that distance was changing the variable in the rise over run because that was used in the calculation in Stellarium somehow to get the angle of the star. Like, he was
And I
way off
definitely
and
was
confusing
wrong.
things.
I definitely did think that this distance was baked into Stellarium, and I definitely was wrong, Cat. Thank you.
Coffee, how would you feel if you didn't eat breakfast yesterday?
I don't know what that question has to do with the conversation, my brother.
Okay, I'll help you. So, like, this is a famous question to show that someone's incapable of like conceptual abstract thinking. Okay, so whenever I asked you to stillman, you said, I don't think it does. You failed the test, right? It's like if someone says,
So,
hey,
so
how
you
would you
thought that
feel
was
if
a
you,
still
I'm
man?
trying to help you out here, my
Did you
guy.
think that was a
Okay,
still
I
man?
think you're accidentally interrupting me. It's okay.
Shut up,
So
coffee.
it's
I
like,
never attempted the still man. That's the point.
exactly.
Shut
That's what
up,
I'm saying.
coffee.
So, like, the example is, how would you feel if you didn't eat breakfast yesterday? And then someone says, but I did eat breakfast. It is literally like the stereotypical, hilarious, inept example of the inability to conceptually assess something. Okay. So, very bluntly, bruh, you're just not capable of having this conversation. So,
All right, that's cool. I'm glad. I appreciate your opinion with it.
no problem, brother.
Yeah, but my contention to this whole experiment remains the same from the beginning. I just think it's pointless. I don't think it actually proves the flat Earth. I just think it gives you guys a good starting point to actually debate refraction.
You can't even describe it in its basic premise. How can you refute it?
Exactly.
I mean, look at
Yeah,
my
we can't
PTRs. You can run through them. You could read it out and see if I
Oh my
explain it to myself correctly.
food. I'll be back in a minute.
yeah,
Coffee,
coffee.
can you
I
know that
still say
something's
just do it
wrong if
and
you
show your
i-
work the way you want it to be
can
checked.
you know that something's wrong if you don't understand it?
I mean, no.
All
Right?
right. All right. So that's why, like, in good faith, I was just asking you to stillman it, right? Because it seems to be this recurring situation here where eventually we find out, wait, are you not even understanding the base concept, right? Then you use the word arbitrary to describe angles that were being taken. So it's like, I just don't think you understand it. So I think that you are disingenuously saying it doesn't disprove the globe. Like you 100% don't know that. You just believe it's a globe. Therefore, you know in your mind nothing can disprove the globe. Therefore, this can't disprove the globe. And that's really all you need to know.
So what's it? I'll ask you. Did they predict the occlusion timing?
Yes.
Well, he predicted a clock
Based
time
on
and
the
went
angle.
outside and to go see if the actual
You
star
said
occludes at that
earlier.
time.
We told you that the guy did.
You said earlier that yeah, angle equals time. I get that. That's it. So when we plane trigged it out, the angle was closer to our angle than it was to what the globe would predict.
So you can obviously do that in reverse, right? Coffee. I could just get
So
the
you
angle.
predicted the angle and not the clock time.
Oh my god, bruh.
Angle equals clock time.
Yeah, you said
No,
given the
no way.
time that this star was occluded, if the Earth is flat, then the angular height should be x. And then as a globeurfer, I say if the star occluded at such and such time and the Earth is a globe, then the angular height should be y. So how do we distinguish between the two?
Exactly that way. We use your height and our height, and we see who can derive their distance and elevations closer.
Yeah.
So you
Does
could rather go
anybody
that
else
route
have
than
a?
predicting the occlusion, rather than just saying, hey, this
We
angular
predicted
height
the
should produce
occlusion
this
because the
clock time
angle equals time.
on the flat Earth. This
Yeah,
altitude should predict a clock time on the globe Earth. And they're
yeah,
just going outside and saying, hey, let
yeah.
me see if that clock time matches up.
That's exactly what we did.
Bro, you know y'all ain't do that. Stop it.
Oh my god.
Coffee. Coffee, you said earlier when I said, well, you know, angles equal time, right? And you said, yeah. Do you not get that part?
Yo,
Because I
Alan,
can.
the reason that I say you guys didn't do that, because I asked Mike verbatim earlier this morning, and he told me specifically he didn't do that. He said, I don't, it doesn't need any predictive measure because if once we do that, we're thinking of models, and he doesn't want to be thinking of models. If anybody was here earlier can confirm this.
Coffee. Do you understand that number one, my buddy Goose already did it predictively how you exactly want it. But that method isn't even necessary because you can always reference where the star once was if you know the peak. So it's like that's not an issue.
Yeah.
You could go out of your way to make the prediction and do it yourself like that, like my buddy Goose did, exactly how you're describing because angle equals time. So that's exactly the same thing. I don't know what Mike said or whatever earlier, but I know that what you can do, like knowing that angles equals time, and it's not really super meaningful to derive everything first if you don't have to, because you could just reference it later and then derive your distance and mountain elevation based off of that, and then see which one is closer, and that actually turns out to be the prediction, and like that turns out to be the meaningful aspect of it because no matter what you do, that's gonna like that determines the actual closeness of the of like who's the quote unquote winner, right? Because the angle itself, right? Like if your angle corresponded to globularity, you should be able to derive your distance in the same way that we're doing it. So ours, there should be no geometric relationship with the mountain peak at the higher elevations that it is at, and the true position, using that as a light source relationship where it's like, you know, physically being blocked where it's no longer going to be able to be refracted. And it's like it just so happens that the timings that when the stars are lined up with that angle, that's when it's no longer visible. And so so we have two different, you know, angles to use for our predictions to derive distances, and we can also derive the elevation
Yep.
like that. And so that's what decides
the meaningfulness of this, because the angle doesn't really tell us much, and sometimes the angle's close, sometimes it's off, but it doesn't really, it's not the deciding factor when the important part of it is, okay, suppose somebody only gave me an angle and an elevation, or they gave me the choice of two angles, right? They gave me a true earth, I mean, they gave me a true position angle at the peak location, and they give me a refracted globe angle, and they say which one of these is going to derive my distance. Which one would you predict makes the correct distance predict, or which one correctly gets closest to the distance? What would your prediction be? That's the meaningfulness of this.
So the difference between the true position of the star and its refracted position, correct?
Yes, we are referencing the true position when it intersects with the peak. So we're referencing where it's at with the peak.
Perfect. So it all falls down to this argument of refraction at the end of the day.
No,
Yeah. I mean,
no.
how it corresponds
Well,
from
okay, so I can see why it's like why you would think that. And when I went over the spreadsheet earlier specifically, I can show the difference in occlusion timings versus the refracted position, where uh, where the measurement, quote unquote, proves the globe, and the only way that it would quote that the measurement even was able to happen at that time was because the true position intersected with the peak. So that proves our premise there, and the measurements come out to be pretty much indistinguishable from one another. So I know that when they have refraction, and there's a 20 to there's like a 10, 20, even 40 arc minute angular difference between them in position. I know that that's just made up.
Yeah, real quick, I just want to commend both of you, especially you, Alan, for their patience. Both you guys have kept your tempers, in check and everything. So, just wanted to say that, man. Hats off to you guys, and great presentation, Alan.
Thank you,
yeah,
sir.
overall, these my guys. It's never gonna be no disrespect at the end of the day. And yeah, I appreciate it.
Yep, been a pleasure as always. But yeah, that difference in angular position really showcases, and then sometimes when it's actually off and it gets the star gets occluded higher, than then it's just like that's not good. But you can see uh, in that angular difference in the positions, like the where the refraction correction is just like, hey, this is what it had to be, and this is what we just made it. That's how they admit to how they derived them in the first place, where they input the globe, assume a bunch of conditions, just do a bunch of integration, hit up your boy expansion series, just do a bunch of fancy math stuff so that they get a computational output that says that says like, okay, hypothetically, the star is here, it needs to be here if the Earth's a globe. What numbers do you need to put into this angle to make it equal what it needs to be for a globe? Like, you can really see where that shines in that angular difference there. Because the only way they even got the quote unquote globe measurements, which are just ambiguous measurements, really, because like I said, they're indistinguishable. But the only reason they even got those is because the true position intersects with the peak,
Yeah,
and the,
because
and, and the refraction difference, the angular difference between them is like really really tiny. Even though the refraction coefficient is large, so like it's a dead giveaway. The physical intersection doth have occurred. I think anything over 10 arc minutes is unreasonable AF. I may even go as far as to say 8. Anything over 8 is fucking you're tripping.
Yeah, so personally for me, when I looked at your graphs and some of Mike's first stuff from his presentation, right? Everything looks spot on correct. The shit was, right, when I look at John's work, right, it's also spot on correct. And the only difference I find between those is just the refractive values.
Yeah, but did you notice that even with the refractive values, the elevation differences, like it doesn't help, you know what I mean? Like it could be any angle as long as it's not the one that we're referencing because that's ours. And it doesn't get the same, it doesn't get a result that helps prove the globe. In fact, it starts to get results that contradict it.
Yeah, no,
Like
But it's
John's method proved the
arbitrary.
globe, matched the globe to the England time, spot on. It's just that it changed the refractive values that he was using. I believe he was, like I said before, he was using 4.1 arc minutes for the celestial refraction and 1.7 for the terrestrial.
yeah, so I don't disagree about the angular position of the mountain or whatever. In fact, that's why I use the time that it was actually no longer visible from Stellarium.
Yeah, no, I figured that. That's why I'm like, we should tie it to a real world observation after the fact, right? We do the
Oh my
calculations
god.
beforehand and then just
It
go
was
outside.
coffee. The timing is the exact same. It was the same time for everyone. So at the time that it was no longer visible for Mike, it was also like with the true position, it was also simultaneously at the same spot for him angularly, at 217 or whatever or 219 or whatever it would happen to be, or sorry, 222 actually, because the time is the same thing. So we know exactly where it was with a real world observation, and we're comparing the two.
Yeah, no, but that's after the fact, right? I would rather us
Dude,
beforehand do it and
it's
then
okay.
check to
My
see if the
buddy did it
occlusion time
beforehand.
just matches.
Yeah, my buddy did it
I
beforehand.
mean, at this
No,
point, we could agree to disagree. That's this is
no,
100% cool, my guy.
well,
Uh,
well, dude, no, dude, like we keep circling back to the same thing, and then you're like, but you're not predicting it, and it's like you forget my buddy did that though. He manually did it. So
Right, it works both ways, man.
so the real power in it comes down to, can you get back to the observer distance, and can you derive the elevation? So just that is the important part.
yeah, that's your opinion. I just feel like it goes back to actually predicting a occlusion time.
We did
It's your
we did
opinion
with the
now.
derived angle, because angle equals time. So you even agree, coffee. You know what's up, brother.
No, because I mean, angle equals time, but each variance of it for each model are specific to different variables, right? You use different variables to compute a different angular height for each model.
Yeah, which
That's
is going to
that,
correspond to a different time. So we're good to go, brother.
Yep.
that's the shit. John's calculations corresponded to the same observation time.
And yeah, I don't dispute that at all. That's our premise. And when we when we derive distances and elevations with triangles off of that, then we don't get the measurements that agree with the globe.
Yep.
Yeah, but it has to be backwards derived, right?
Well, I say backwards derived because it's like stuck in me vernacularly. It's not actually backwards anything. It's just solving a triangularly regularly, because we have two variables of the triangle. So we're not like backwardsing it. I constantly say it like that because I'm retarded. So
And I went over that with you yesterday
I know.
repeatedly. I went
Oh, so
over that with you yesterday, Coffee, repeatedly about how this was not backwards derived, that the rise over run that gives you that flat earth predicted angle. Like technically, you want to do an experiment, pick a mountain peak, know your distance to it, do the rise over run. Then you go to the peak of that mountain, and then you're going to have to look for a star that would have Can't you figure out your initial bearing or whatever, and then go watch, like what Goose did for when a star would be occluded at that point? So there's, you go there, and you can see what the angle would be to that star. Does it match the flat Earth? You know, how close is it to that just plain trig of rise over run to the mountain?
Yeah, not to mention Jesse, quote unquote, predicted it too, right? He
Oh,
built a
was Jesse's a
simulator.
prediction?
Well,
He did it that way
so
too.
he had to give the distance to find like the ratio and stuff, but like you could look at it like that if you wanted to. But basically, he
Mm.
used the methodology of the ratio of the distance and elevation to get an occlusion timing, which is exactly what we, that, like, the premise works. It sounds, he derived a triangle that he thought proved the globe, and then doesn't take the analysis really any further than that. When we look at the elevations and distances, though, it's, we're literally we're like indistinguishable. And then when we look at the other examples, it's more noticeable where the discrepancy is that the globe isn't globing. It should be the other way around. The flat Earth should be the divergent one. We shouldn't be matching the positions and uh, and elevations. We should be off. We should be overshooting, but it's the globe that's overshooting. It's specifically the refracted globe that's overshooting.
I mean, using your math for the flat Earth, you guys should hit spot on most of the time, right?
Hell yeah, brother.
That's crazy. I can't believe you just said that. Do we have any other Globers who wanted to chime in at all?
Yeah, I don't know. You got Hanson down there, but I don't think your interactions were any good before in the past.
Mm.
But if you want to, I mean, feel free. I sent him an invite.
I mean, really, Alan's explained it very, very thoroughly here. So
What's up?
I said you've explained it very, very thoroughly here, and this back and forth, just kind of goes to show that the points that you were making, you covered each point very well. So commend you.
It's for the boys, and it helps me every time too, because like it's a complicated subject, and it's like, how do we, Linnell was saying earlier, how do we get it to the people?
Right.
And one of the things that was mentioned earlier about, like, abstract comparisons and stuff like that. Well, like, sometimes you're communicating with someone where that's an issue, and like, how do you, what could be done to better articulate it to overcome that in the future or whatever.
Yeah, yeah. I want to see what Bennett thinks about it when he digs into the stuff.
Yeah. Oh, he sent me something he did with Grok or ChatGPT or something that he was messing around with. I'll have to take a look at it. It should be in the Discord in the AI analysis tab. I haven't looked at it yet though. But if
I'm
you
about
want
to
to take
check
a
that.
gandy,
Yeah, I'm about to check it out right now.
yeah, he said he was going to check it out.
How long ago did he get it?
Uh, about a week or two ago, and I think he's like loosely heard us talking about it off and on and stuff. But he just actually asked for like the documents and stuff on it recently. So
So he wanted to wait till y'all got it all figured out before he
yeah,
kind of gambled. I got you. Okay.
yeah.
Yeah, I'm definitely curious to hear his response.
So yeah, his initial thing was, maybe it's just locally flat at Mike's house and it's a coincidence, so it should be repeated in other places. And then so, we've done it in other places. Uh, Mike's done it in other places. Jesse's done it in other places. We've got like a nice spectrum of analysis. My buddy Goose did it at another place. So we got a nice range of measurements now. It would be nice to get some lads from the South, some Southern, some Kiwis, or some Australian blokes,
Oi.
or whoever else is South. It would be nice to get some Southern measurements.
Who's here? Tarek, you here, bro? So we got my man Tarek is in Australia. Let me see if I can get him to come up.
Alan, that's in Ether Cause, or that's in Earth Awakenings, this AI channel? Because I'm looking in Ether Cause, I don't see the AI channel.
It's an Ether Cause.
It is Ether Cause, okay.
Yeah, it's on the left tab.
Yeah, it says
Okay.
AI peer review.
AI peer review, where the hell is that?
Yeah, Alan, I was mentioning to Kat also. I do have an observation lined up. Unfortunately, it's in my cousin's house. So, and when it dawned on me that I had a awesome view from his backyard to some mountains in the distance, I just didn't know how to identify the peaks, and I was leaving that same day. So yeah, unfortunately, I saw the mountains in the day, and I'm like, wow, what a view! Holy shit! So I see the like, and then I'm like, fuck. So I got my coordinates and shit. I was like trying to look up elevation, but then I was like, how the fuck do I identify these peaks? I'm like, how? And I, checked my, my, I know I was definitely looking north or maybe a little northwest or whatever, but she did mention to me the peak finder. So hopefully I could get that going. I could get that data for you guys. Hopefully soon. I don't know, maybe within a month, hopefully.
Oh, nice, dude. Yeah, that'd be awesome. And yeah, Peak Finder's dope, especially the phone app because you can have it overlay through your camera, and when you take screenshots and click on the peaks, it takes screenshots of that for you. So it'll back up everything, with just like one touch. And when you do that, it also gives you like the relative elevation and distance to the peak. So you'll have like a nice baseline of like what you're looking at.
Oh yeah, and I did try. I think it was off of Google Maps or whatever when I was trying to find like what trying to identify the peak. I was trying to like use the measuring tool. If I'm correct, because I did own a house, right? Because if I was in Allentown, and if I'm looking north, I'm looking like towards like Poconos area, right? So I owned a house up there, and I know that there was some game lands like right behind, like a little west of my house, which looks to me as if that was like the position that I was looking at. So it seems like it may be somewhere around 50 miles. So it should be a pretty decent one.
Nice, nice. That's awesome. Yeah, I mean, honestly, any distance is good to go, and it's cool to see the effects of because there's like more to the analysis than just like the angular stuff. We're getting a good grasp on the relationship of refraction and how much is like the overcompensation refraction and how much is like a reasonable amount for the physical intersection. So any data is good data at this point. So like if any distance is you know
Yeah, unfortunately, what I don't have is like a really good zoom cam or whatever. So maybe for now, I guess I'll try it with my iPhone. But she also did give me a great tip. Just take a nice picture in the daytime as to where you're gonna be positioned at. So that way you can like overlay. So that's that I'm guessing that's what I'm gonna do for now, unless I could grab like borrow a camera from a friend or whatever. But I do want to get the data first, and if I could obviously refine it, some other time when I could get a better camera.
Oh, dude, if you just get a raw data and it's like and your peak is like definable enough, if you just get that video to me or Jesse, like we'll figure everything out for you.
Nice.
Yeah, we just need the video, your location, and what peak, and we can do everything else. We go star hunting.
Alan, you said one of your homeboys did the predictive measure and went that route, right?
Yep,
When you get a chance, send me a link to his work if you can.
absolutely. Are you on Discord, Coffee?
I am, but I'm hardly ever on there. I gotta get in there and tap in with y'all.
Gotcha, gotcha. Yeah, he's on Discord. All his stuff is on there. I'm not sure if he's. I don't see him down in the thing, but yeah, all his stuff's on Discord. I can send it. I can send. Are you on Telegram? Yeah, TG.
Yeah, I definitely got Telegram.
All right, I can send you a zip of it at some point. I'll get it from him.
Hey, Tarek, you here, bro? So he just popped up. So I know.
Yo, it works.
What's going on, man? How you feel? Where you been, bro?
Yeah, I heard you guys calling me out before. What was it? Yeah, I've spoken to Alan. I plan on getting a couple of these in the next 2 to 3 weeks.
Oh, sweet. There you go, Alan. You got
Um,
some from Australia, bro.
Nice.
yeah. So
You're going to Perth, right, Tarek?
yeah, so I'm going over the other side of the continent. I don't know if this is interesting. You guys tell me, but I'm sort of looking to do
Sorry,
it
guys,
both
I gotta
east
go.
and west. So as the star comes up and as the star goes
Catch
down,
you guys later.
because I'll
All
be
right, Beastie.
traveling
Have a good night, bro.
particularly areas. And,
You too.
All right.
All right, lads and ladettes. Beast had to go, so I lost the audio for this, and I don't have my normal streaming setup available, so I lost my way to share audio on here. So I'm going to go ahead and wrap up now. Thank you all for participating. I saw I got a super chat earlier. Shout out to you. Let me take a look at that here. I'll read your thing, check it if there's a message. Much appreciated. Always appreciate a good super chat in here. Let me turn the camera on here. All right. Where are we at here? We got, there we go. What's up, lads and ladettes? We got Shalomzy. Thank you, my good sir. Thank you, sir. Much appreciated. Oops. Just closed out our clubhouse. There we go. Stay back. Okay. All right. Thank you, lads and ladettes. We will be back on, let's see, tomorrow's Friday. We'll probably do some Friday and catch up with the Friday Twitter crowd, go over the celestial theodolite and the findings. And then, of course, Sunday, we will be back on Globebusters, where I'll be presenting the celestial theodolite and asking people to participate to help gather more data, etc. So we can go over all that. But yeah, see you guys on Sunday. Then of course we'll be back Monday with Celestial Theodolite Update 14, where hopefully I will have some changes made to the spreadsheet, and we will go over those changes and comparisons and the things that I found since I've made it. And on top of that, oh, there's a bonus stream Saturday with the checks at 2 p.m. Tune into that. I'll be doing a stream, doing a celestial theodolite update for them, giving them the deets. So if you want to check that out and hear more about the celestial theodolite, we will be over there. I've been meaning to do a CT measurement in Australia. I tried at the beach targeting a lighthouse, but I couldn't see the stars anymore at the horizon. Oh, that would be super interesting. Yeah. Let's see here. Let me check through the chat here, see what you guys have been up to. Goose, Bogan, Brett, Angling Alchemy, Shalomzy with the super, Mad Mac, Mike Jones. Shout out to Mike Jones. I miss you, brother. Let's see here. We got Run Boston Bear. All right. Cat, Cammy was out in the chat. What up, Cammy? Sorry I missed you earlier. Mad Mac. Ion's Cat. James Brown. If that's the James Brown, I think it is. That's our lad from Twitter. Welcome, welcome. All right. A press. What up to your girl? Driving around in the Ferrari, I hear. Big Pine. Hobbs. All right, Hobbs. Hopefully you're able to get that celestial theody observation. That would be super dope. No one as of yet has been able to do an intersection with a man-made structure, so that'll be cool to see that if you're able to get that. And of course, we got KIC. Shout out to Kingdom in Context, the homie Sean. I'm pretty sure that's Sean, if I'm not mistaken. And Tonith Coriolis, my good sir. And D Not. All right. We'll see you guys on whatever day it is. Friday. We'll see you guys tomorrow night. Have a good one.